All right, so we're gonna try something a little bit different today, and I'm gonna pull up my video here, and I'm gonna pull up some of my different things. Let me test my information here. Okay, I've got that. Test and test. Boom. All right, I can send information on both sides. Roaster in the wild, how's it going? We are working on. Now, I do need to pull up a different one of these, so let me get rid of that for 1 second. Go back in here. Go into here and pop out this chat. And I think that's going to look more like what I want. Yep, there we go. So now I just have to point at that source. Give me 1 second. And then we will be off to the races. Studio, YouTube's. Ah, damn it. I just messed that whole thing up. Hold on, guys. That wasn't what I meant to do. Fucking A. Alright. Twitch chat back. Put that up there. Other chat, YouTube chat, will be this other chat. My bad. Alright. Clean that up so it's the right size-ish. That's good enough for government work, huh? What do you guys think? That looks good. Alright, so what we're doing today is a little bit different. Yeah, I'm going to be doing some co-working where I'm going to be working on my own project stuff. But I thought it would be fun for us to go watch one of our older videos. I recorded this live while I was in a Discord so people could ask me questions. I'm also going to be sitting here, so if you guys have questions for me, feel free to ask. Today's topic is networking primer. So we're going to go over networking outside of Linux, but I will be touching Linux as we go, yes. So, Producer Wolf with the raid. Thanks for the raid. Hopefully this stuff's getting useful. Yeah, Cheeto, I'm trying to, I find that when I co-work with you guys, I get a lot of stuff done. And, yeah, let me move this down. I just don't want this in the way. The YouTube chat here. I just don't want it in the way of everything. So it's just you have these sizing limitations of kind of what you can get away with, you know. I wonder if I can make this bigger. Let's see. Can I zoom in on this chat? Oh well, that's fine. We're good enough there. All right, so I'm gonna run this video. I'm gonna be sitting here, so if you guys have questions, feel free to type them in or message me, and I will try to pause the video and answer them. But this is what I'm working on. I'll be in a different window, building my training out like I've been doing. So of course, you know, just ask me questions. Let me know if you guys have anything you want to talk about. Otherwise, I'll be sitting here listening to the same thing you guys are. This is me from a few, I don't know, this was about a year ago. Yeah, Producer Wolf, how do you like Proxmox? I know a fair amount of people that use it. You guys could probably tell my voice is still just not doing great. These allergies and or just, it's just bad right now. So, Debian 12, nice. Nice. Yeah, Proxmox has good integrations with tools that people like to use, like Terraform, and it has better Ansible integrations even than my XCP-ng does. So, there's all that. So there's additional value there. So, all right, I'm gonna start the video. Let me know if you guys can hear it okay.
Live in the background there. All right. Yeah, hey everybody, we'll give it a few more minutes to start, and I'll go ahead and drop that over as well into the stream. I'll just go ahead and put it like this. That's fine. You guys can see me. That'll be fun. All right. Get that stuff out of the way. You guys should be able to hear me. Roadrunner, give me a thumbs up if you can still hear me over there. think you guys should be able to hear me. Yep. Okay. Good. 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 Oh, you guys should be able to play sounds too in Discord. You guys know how to do the sounds right at the bottom. You got the little musical. I'm pretty sure that's gonna come through on the live stream too. So yeah, if you guys want to put any of that stuff up, you can. All right. People online are probably like, "What the hell is this guy talking about?" We've got Discord. We're in there talking shop, and we are doing the professional Linux users group. This is like kind of our normal meeting time, but I'm also going to show it on here for people on Twitch that just refuse to get on Discord. So if you guys want to troll me on Discord with claps and duck sounds and stuff, you guys can certainly do that. Also, made even funnier by the fact that I really can't see my Discord right now on my monitors that I have up. So that's kind of funny. That'll be for my jokes when my jokes don't land. All right, one more minute and we'll get going. And again, this isn't like I don't really save these VODs off anywhere. So if anybody is interested in this, I'll do a more closed down version. And I'll record it and put it up somewhere, kind of like I did with the high performance compute stuff. So that'll be something available to you guys that want that. All right, give it about 20 something more seconds. I'll go check on Discord in case anybody's got any things. Yeah. Now you guys got all the sounds. I really thought there was a womp womp. That'll be for when my jokes don't land. How's that? And I don't know if you guys can hear that back in through Twitch, but that's funny. All right. All right, and then after this, in the Phoenix area, we're doing a meetup. Not a meetup; it's not a real meetup, but it's we're going to be doing a like a game night tonight. So some of my friends that are more gamers are going to come over. We're going to do some gaming, and if not too many people show up, we're just going to go to a game store and look at retro games and stuff. And for you guys that know me, I have quite a few, like probably an unhealthy amount of board games and stuff. Some of you guys have seen the pictures of my board game wall at home and in my board game room, and the wife built the shelves for that. Her and her dad put together some really nice shelves. All right, well, let's get to it. I don't want to burn up too much time. Normally the first few minutes.
Now remember, guys, I am still sitting here while we're doing this, so while we are watching a recording of me while I work in my other windows, if you guys have questions about what this guy online here is talking about, that's me, and I can tell you any of the stuff. So let me know if you guys need any, if we need to jump over to anything and talk about anything. All right, back to it.
Of the professional Linux users group that meets on Saturdays, we would kind of just talk around and see what's going on. We'll skip that today because everybody's here for the networking primer. I'm just going to kind of brain dump for a few hours on stuff around networking. I'm going to pull up some stuff. We're going to be looking at Wireshark, so we'll be looking at stuff in here. We'll be looking at stuff inside of an actual Linux system, right? We could also look inside of Windows systems too if we want to, but anything networking is going to be on the table for today. All right. Here's some quotes to get you interested. If you already weren't interested, let me tell you why I think you should be interested, right? So I get that not everybody wants to be a network engineer. A little funny story about me: I didn't want to be a network engineer. I got my CCNA when I was still in the Army. I got out. I was a network engineer for 2 years. Almost 3 years. I moved up. I was a LAN tech, and then I became a LAN 2, and I was in charge of the firewall and wireless for a pretty good sized school district here in Phoenix. And I just didn't love it. Like I was like, this is okay. And then I did some networking and monitoring over at GoDaddy, and then I really got into Linux. Right, I've been heavily into Linux for like 20 years now. So, but that being said, no matter what you do, every device you have touches a network. So the idea that the network should always just be a cloud that we don't understand doesn't really sit well with me as an engineer. Like I think we should understand, any sufficiently advanced technology is indistinguishable from magic. We should not think of everything happening magically. We should have a way to go and understand it, okay? So we'll talk about the types of computer problems, right? This is just some XKCD jokes. I think XKCD is great for engineers to reference because they have some really good stuff. And we're going to talk about, why do you want to know these individual pieces? Well, there's a lot of good kind of engineering knowledge that will help you troubleshoot things. It'll help you in your, probably ability to just kind of grasp what's happening in a network and stuff like that. And it'll greatly help you to resolve issues in a system. So let's just say those are the reasons that I think that you should be interested in this. All right, so here's the topics today. We're going to talk about the simple communication model. We're going to do a lot with networking. There will be a whole lot of stuff with networking. We'll talk about the 3 types of addresses that we use. We'll talk about how and why we subnet. I'm going to do some decimal to binary conversions, stuff that may seem a little basic and simple, but it's important. Not everybody sat through a class and learned it, so we got to learn it. I'm also going to point out while we're doing that I don't expect everybody to be an expert in that right away. It takes time to learn some of that stuff, okay? And then we'll do OSI stuff. OSI is the model that most of us use to go through and think about everything in networking. So I'll try to fit most things to the model. Not all things will be part of the model, but we'll talk about what happens at each of the pieces. We'll talk about, heavily on these bottom 3, the bottom 4 rather. And then a little less physical because I decided not to go as far into data transmission as I was going to, but if any of you are interested in that and want to talk about that later, we can. And then presentation and session we'll kind of gloss over because there's not so much in there. In fact, the top 3 aren't as important, but the top one kind of becomes important again as we talk about some of the communications and security standards. So we'll get into that. Learning AWS, I think I cruise into DevOps and network. Yeah, networking's huge. So hopefully this gives you guys a good foundation and gives you a place to go. All right, so here's our course objectives. If you're just like, hey, Scott's sitting here talking, he's got his Linux group on. I think you guys can, somebody make some noise for me. I think you guys got some sounds you can push. Anybody that's on our Discord can jump down in there and play the sounds if you want to and talk on there. There you go, clapping and all that good stuff. These are the things I want you to know. You don't have to know everything, right? It says right down here, this is not about becoming an expert. Even if I thought you could, even if I thought I was capable of teaching most people this, I don't think I could make anybody an expert in 2 hours even if I wanted to. This is kind of like a survey. This is high level stuff. It's the buckets that the things fall in, and hopefully it's a time for you to ask me questions because I've been using this stuff a long time, so hopefully this stuff kind of makes sense for you guys. And we're approaching 100 students in our thing over the last, I think I've probably had that open for about a month. So we'll describe the components of computer networking. We should know at the very base level, like the different pieces that go into each of it. Understand why we subnet larger networks into smaller ones. You've probably heard a lot about subnetting. You've probably heard about fixed length and variable length subnet masking. Maybe you've just heard those terms. Maybe at work you have an IP address manager, like an IPAM system, but maybe you're too scared to get in there and you just let the network team give you an IP address range and then you just hope that your stuff's in the network range. We'll talk about why we subnet things and why those things work the way they do, and then we'll just kind of talk about that. We'll talk about the flow of data through a network. This is kind of important. The data flows down, across, and back up through the stack on 2 different hosts. Also in between there, it's also flowing up to each of the layers of the devices, but we don't need to worry about that for now. And then I want you to know that at each layer, the device talks across to the other layer in a way that it understands, almost like we're addressing an envelope or something. So there's a term that goes with that called protocol data units, or protocol data units, I don't care how you want to say that, at each layer of the OSI model. I want you to understand what those are and what the implications of them are, and we'll look at them technically as far as the headers and the footers that are applied as we talk about each of those, all right? And then we'll understand the term modularity and how it applies to the model. If we understand modularity and we understand the model, then we know what we can change and what we can't change. With modularity, if it's kind of like it's back to that idea of magic, right? Where's he at? I don't know how to work magic, but I do know how to work engineering. And once I understand a thing, I know how I can change the components if they're modular components. So that's some of the things that we'll kind of get into here. Again, out of scope. This is not expected to, this is not designed to make anybody an expert. It's designed to help you figure this stuff out. If anybody wants to join our Discord, you guys are welcome to go down there. Here's our Discord link. And by the way, people on Discord, if you guys want to ask me.
Yeah, this isn't a restream, so I'm not going to be calling it a restream. I'm sitting here working while you guys are watching this. So you could ask me questions. A restream would imply that I was not here. I am literally sitting right here watching this and doing stuff on my other stream, so this is not a restream. So yeah,
Any question you can, I don't mind, as long as you don't mind being on on stream here talking, just interrupt, because guys, I've been teaching for 15 years. I know that I move fast. I know that when I start brain dumping, it goes fast. So if there's something you want to know more about, just stop. Okay? All right. So let's go. Here's the basic thing. Some of you might have even been on stream earlier. I was talking about.
All right. Well, we are gonna fix this problem. Give me a second here, guys. Got a problem I need to go solve. Where is my... Is that down real quick? All right, well, we're just gonna whatever. Leave that there. You guys should be able to see it. All right, we'll leave it. We'll let it just be a problem. All right, back to this.
The simple communication model. The most simple thing that can happen for communication to occur always has 5 components. There's no simpler model known to man that has less than these 5 pieces. These 5 pieces are always there if communication is happening, and there's no simpler form of this that is an effective type of communication. So we have a sender, a receiver, a message, a medium, and noise. Those 5 things always happen. The sender encodes using a protocol. The term protocol means the rules that govern communication. That's all it means. It's a simple term that extrapolates out into the rules that govern communication. So if you hear me say protocol or you hear somebody else say protocol, they're using it as like a wrapper around the way that communication happens. So if you've ever heard that term and just been like, man, why does everybody talk about the protocols? That's what it is. It's the rules that govern communication. We have the sender. It's going to encode a packet by some protocol to be transmitted across a medium. Right? The medium is either a physical cable in our case with electro or optical signals, or it could be free space. It could be air of some type via some type of radio, electromagnetic wave is what makes a radio, or some type of laser optic wave that typically is line of sight and deals more with environmental factors and that kind of stuff, right? There's a message, again, that's encoded. It's traveling across the medium. And then despite our best efforts in all the world, we will always have noise. There will always be noise, right? If I come down here, there's my stuff. There's my noise. There's always going to be noise in a system. You can't get rid of it. So these 5 pieces are always going to be there. So if we can understand the individual parts and what's going on in here, it's going to help us to do communication. I mentioned this earlier today. There's a 6th one that's required if we're doing what's called effective communication, which is a feedback loop. So something is being sent back to let the sender know that the receiver heard. That's a different concept. The simple communication model is these 5 pieces. They'll always be there. All right. So let's talk about some fundamental terminology. This will be like level setting. Some of these things you're going to see again. Some of these things you're not. But I just want to make sure that everybody understands. Because when you look at networking diagrams, people start hitting you with the TX and the RX, and you're like, right? Like what the hell's going on? And when we start looking at packets inside of both Linux and Windows operating systems, which is most all operating systems out there, you're going to see TX and RX. TX is always the sender. So back to my old model, the TX side is always the sending side. It's the transmission side of the communication link. The RX is always the receiving side. Makes me think I probably should have added simplex, half duplex, and full duplex, but that's fine. We won't worry about that level of lower communication. But there's always a sender and a receiver, right? That's how we talk about them. When we get up into wide area networks and specifically around networks that we don't control, right? We talk about systems in our control as being autonomous systems. And AS is an autonomous system. I control my network at home. You control your networks. The ISPs between us control their networks. That's known as an autonomous system. Okay. When we meet with one of those systems, right? That's typically called a wide area network. There's a lot of ways that we can determine what's a LAN and what's a WAN, but one of the best ways in an organization, from like a company standpoint, in an enterprise, is the LAN, the local area network, is something you've bought and you own, and it's a sunk cost, and you're just paying to keep the electricity flowing to it. A wide area network is something you lease, typically. It's something you lease, and you will never own it. You are always just going to be leasing that circuit from somebody else. Now, that's a very high level determination of those things, but that's a good one that's kind of good to know. All right, now when we talk about the interface from the WAN that we don't control through the LAN that we do control, now we're talking about how do we connect. And typically you'll have some kind of data circuit equipment and data terminal equipment, right? Data circuit equipment is typically on the vendor or the ISP side, right? And it's responsible for the clock rate of the serial line. Yeah, Rodom, you probably should be able to hear in both, but you guys are welcome to go and do this however you want. Okay, yeah, you guys online should be able to hear me. You guys there? Okay, good. All right. I'm just trying to do this, to two audiences, but with different levels of being able to communicate back. DTE is your data terminal equipment. It's typically on your side of the connection. All right. Now, right where any wide area network and local area network, or multiple local area networks or multiple wide area networks come together, between those autonomous systems, there is always a demarcation. The demarcation is the point that ends your responsibility and my responsibility begins, or where my responsibility ends going out and your responsibility begins. If any of you have ever called, this is one of the most maddening experiences any of us will ever experience, but you've called like your internet provider, and they're like, well, I can ping the modem, or I can get to the modem, and you're like, all right, well then it must be on my side. But before all that, they made you turn it on and off like 17 times, and you're like, just tell me what's wrong, Anyway, so but we can't do anything about it. We can't troubleshoot past what is under our control. So we need them to verify that they're at least getting a link to us, right? And then another term that's just a good level set term is a metric is a metric is any unit of measurement used to differentiate a system. So we might say, I'm going to use this metric for I'm going to use the metric of bandwidth to determine which of these links is the best way to get somewhere. And I say, okay, well, I'm going to use the metric of latency. Those are two very valid metrics, but we should know, one, that metric just means a form of measurement, and two, we need to know, like, if we're talking to each other and I'm like, this link is better, and you're arguing that that link is better, but we're using different metrics. This is why, by the way, it's so useless to argue with people online, is because we've never agreed to the fundamentals of how we're going to come to a conclusion, right? Like, I'm going to argue this point, you're going to argue that point, and we're going to do what's called talking past each other, right? It's the same thing with communication, and same thing with working with other engineers. It's good to know what metrics we're using to measure something, because you're gonna find that you can get to solutions faster and better if you decide to work a certain way. All right, so that's some fundamental stuff. No questions on that? All right, we'll keep going. So there's three major types of addresses that we care about. There's three major types of addresses you're going to see in the networking world. There are probably a few others, but the three primary types you're going to see as a systems engineer, as a network engineer, are these right here. At layer 7, you're going to see DNS addressing. Most of us have probably used DNS addressing. Maybe you came to Twitch, maybe you've gone to some code wars or something like that. We got a little code wars battle going on in the Discord, so that's kind of good. But DNS addressing is the mapping of some readable name to an IP address. It can be an IPv4 address or an IPv6 address. We're going to break those down here in a little bit. But it is our way of remembering. I can remember Google real easy. I have a little bit harder time remembering that. I may be able to remember that for a few days, but I can't remember Google and Yahoo and MSN and Twitch and Amazon and all those like that. It just gets to be too much, right? So DNS addressing is the way that we map human readable addressing, right? IP addressing is a logical hierarchical addressing that happens at layer 3 that allows routers to do path determination. Routers do two things: path determination and packet switching. Path determination is based on your IPv4 or your IPv6 address. Routers will make a path determination out of their routing table to where things are going, and if they don't know what to do with a packet, they will send it on to their gateway of last resort, or what's sometimes called a default gateway. However, this is a little fun fact about Cisco that not everybody knows unless you've done a lot of Cisco. If a Cisco device does not know what to do with a packet, it simply drops it on the floor. And you might say, oh, I've never had a Cisco device do that, because you've always set the gateway of last resort, or somebody has set that for you. But I assure you, if you don't have a gateway of last resort or a way for your device to send something to, like, hey, I'm going to phone a friend, I'm going to send this to another device, it will drop it on the floor every time. That's the behavior of Cisco devices. Behavior of most networking devices, but Cisco's kind of painful when it happens, right? And then the one that, you're not going to use much, you're not going to play with this much or see it, but your system sees this all the time, is MAC addressing. So I didn't go too much into IP addressing because we're going to break that up ad nauseum later. But MAC addressing is a hardware address that's burned into the network, burned into the MAC or the NIC of every device that you have. Now, if you've got a virtual machine or you're dealing with something up in the cloud, those MAC addresses can be generated. We can also spoof them very easily, especially with a lot of our wireless devices. We can just change what MAC address it's advertising with. But the thing about MAC addresses is that all of your devices see, within certain rules of how forwarding and broadcasting happens, they see most of the other MACs that are on the same network segment with them. So they see all of that's going on. And they use a tool called ARP, Address Resolution Protocol, to figure out and keep ARP tables, Address Resolution Protocol tables, of what's the mapping of the IP address, or in this case the host name, with the hardware address that is known to it locally. Yep, some people like the please do not throw sausage pizza away. When I get to those layers, we'll talk about them a little bit, and then I think as you do more of them, you will probably less use the acronyms, but the acronyms are great when you first start. All right, so those are primary parts of addresses before we dig into we're going to get more into all of these addresses here in a little bit. All right, so let's do a quick binary rundown. If you guys have never done anything with binary, I'm going to show a little bit of this. People that came on earlier when I was kind of like running through this and prepping the last little bit, I did draw this up a little bit. But let's do some binary information around the IPv4 stuff. Like, this is the stuff that a lot of people struggle with, but allow me to give you my 10 to 15 minute primer that I think makes this work the best in my head. I'm just going to draw 3 lines right here, real quick. And on those 3 lines, I'm going to draw some numbers. All right. Now, can anybody tell me what that number is? What does that equal? While you guys think about that, or what that answer might be, I'm going to draw some stuff over here. King Bun said 579. That's true. See if I can count to 10 on stream. All right. Well, what this is a numbering system we've all used many times. You, Moon, that's not wrong, right? It's not wrong. But let's think about something. Some of us probably learned this back in like 6th grade. I'm just going to step you back for a second. I'm just going to step you back to when you were a kid and you learned this. But I'm going to use some technical stuff. And again, it's going to be technical jargon. It's going to sound real pedantic, like I'm overly concerned with the use of words. But we have to get to kind of the heart of this, so we have to use some of these words. So, there are 10 states of nature in any one of these. So any one of these positions here can exist between 0 and 9. Does everybody agree with that? In this numbering system, that I am not tricking you in any way, I'm just showing you the numbering system we tend to use, like if we were counting money, has the characters 0 through 9, which is 10 states of nature, meaning that there are 10 possibilities that can exist right here. That is what is called a base 10 numbering system, absolutely. So this is a base 10 numbering system. Now, because we are representing 10 spaces over here, this is 10 to the power of 0. So this is the tens column right here. Sorry, this is the ones column, because anything to the power of 0 is 1. So this is the ones column right here. This next column is 10 to the power of 1, and anything to the power of 1 is itself. So this is the tens column. And right here, this is 10 to the power of 2, so that makes this the hundreds column. Now, earlier when I asked you guys what this number was, what I was looking for is kind of what probably some of you, I mean probably all of you went like this immediately, is this is actually 5 100s, it is 7 tens, and it is 9 ones. And you did that in your head without even thinking about it. But that's how this numbering system works. Now, we're down here for this because we're dealing in ones and zeros going across a line. The numbers we allow for that are 0 and 1. We only have a 0 or 1. There's only 2 states of nature. There's 2 states. You can only be a 0 or a 1. Those are the only options you have. So if that's the case, now 2 to the power 0 is the ones column, because 2 to the power 0 is 1. 2 to the power, 2 to the power of 1 is itself, so that's a 2's column. 2 to the power of 2 is 4, 2 to the power of 3 is 8. That's where these numbers come from. They're not made up. It wasn't like some guy that just knew math better than all the rest of us said, that's how we'll do binary. All right, so now since we're looking at this, and it's 8-bit, it's called 8-bit, because there's 8 bits to each of these, dotted, decimal. 8-bit dotted decimal, I know it's hard to read, but 8-bit dotted decimal is what we're looking at here. So each of these represent 8 bits, so we have them all down here. So if I told you that all of these were set to 0, what number do we think we'd have down here? We'd probably have the number 0. And if we were to turn them all on, right? The states and base 10 are the numbers 0 to 9, or there are 2. Yeah, that's absolutely right, Yumun. Absolutely. If we were to turn all of these on, there's a little trick we can do here. It's 128 plus 127, because 128 on plus all the numbers before it can only add up to 127. 128 plus 127 is 255. So everything that can be represented in these numbers is 0 to 255. Which is, by the way, why you have between 0 and 255 in any of your locations on your IPv4 32-bit, and again, an 8-bit dotted decimal format presentation. So, let's look at this real quick. I'm going to do a little bit more with binary around addresses. Let's say 192.160. 192.168. Let's just say like 19 for today. 19 dot, let's go 37. We'll do a fun one. And we'll make this a, we won't worry about the slash to this, but we'll talk about why we need these different things around the page here to help us out. But let's break this 192 that's in a decimal format. It's got a 1, a 9, and a 2 in it over here. How are we going to stuff that down into this? And if you've never done this before, this is the crux of all of it right here. I'm about to show you the absolute crux of how this works. We're going to take that 192 and we're going to ask ourselves, starting from the left, does it have a 128 in it? Can I represent, out of a 192, can we extract out of that, squeeze out of that a 128? And the answer is yes. So we're going to turn that bit on. That's the 128's place. Then if we take 128 away right here, we should have 64 left over. And the next one is the 64's place. Can we get a 64 out of a 64? And the answer is yes. Now we have 0, right? Just put 0 there. Can we get a 32 out of it? No. Can we get a 16? No. Can we get an 8, 4, a 2, or a 1? And the answer in all of those is no, we cannot. So let's do it again. Let's go to 168. Can we squeeze a 128 out of there? Yes. So that's right there, because it's in this section. So then we've got 40 left over. Can we get a 64 out of 40? No. Well, we've got 32. Can we get a 32 out of 40? Yes, with 8 left over. So can we get a 16? No. Can we get an 8 when we had 8 left over? Yes. So we got nothing left, so there's no 4, there's no 2, and there's no 1. Now, if you've never seen that before, that's how that works. Now, I picked this one because it would be a little more challenging. Is there a 128 and 19? No. Is there a 64? No. By the way, if you get lost, that's where I'm picking them from. Is there a 32? No. But there is a 16. but now there's no 8. There was 3 left over. There's no 4, but there is a 2 and there is a 1. So that right there is the digital representation of 19 when you were dealing with 8 bits. Now let's do 37. Let's look at 37 real quick. 37 has no 128s. It has no 64s. It does have a 32 with 5 left over, which means no 16s, no 8s, but there is a 4, which means that we have 1 left. 1 right there. So we just broke 192.168.19.37 down into its binary. Now, there's a few more things we got to talk about that make this kind of mapping that I have here complete, that are going to go into IPv4 addressing a little bit, and hopefully assumes that you have a little bit, right? This isn't a bare beginners type thing, but let's look at this first octet here. There's a 192 in it. To determine what class we're dealing with, there's 5 classes typically. There's a class A, B, and C that you'll see all the time in this world. Then there's a D that you will not see often, and there's an E that you will you'll see D more than E. E will very rarely ever be there. But if I look at this and I tell you that the rule right here in this first octet is that it falls into one of these, can anybody here tell me if this is a class A, a B, or a C network? By looking at this first octet, 192. If it's between 0 and 127, it's a class A. It's 26, but if it's a class B, it's 128 to 191. And then if it's a C, it's 192 to 223 in the first octet. So do we know what class this is? It's class C, right? It's class C address because the first octet is right there. Class C address has 24 networking bits. There's 2 portions to an address. There are the network portion, which in this case is the first 24. So there's 24 network bits. And then in this case, because we didn't give it anything special, there's 8 host bits. Now, there's other bits that we can slide in here later called subnetting bits, but there's none right now. I'm going to show you why we subnet on the next slide, and then I'm going to show you how we do it. But let's just look at this for a second and look at some more of these rules. We've already used this right here, so we're checked on this. And we've used this to determine the network and the host portion, which is left over. But then let's come over here, and I say something about masking. I say that N bits are 1s, subnet bits are 1s, and host bits are 0s. So let's go up here to network bits. All these network bits are 1s for masking. So my mask is down here. There's my IP. Here's my mask. And I go like this, a bunch of 1s, because that's the rule. Network bits become 1s. There's 24 network bits, so here we go. And then I said that host bits become 0s. I don't have any S bits here, so these are out for right now. So there's no host, so in host bits, they're all 0s. Those 0s look like 1s. All right, so there's all 0s. So now we convert, so somebody says, can you take this address and tell me from the default what the subnet mask is? And I say, yes, I can. Didn't we determine earlier that if these were all on, then we would have the number 255? Hey Johnny man, how's it going? We got 255 right here, so all the bits are on. We've got 255 here. And then we got 255 here. .0. So if somebody was programming a 192.168.19.0 network into their system, like you were putting it in, like if I went and looked at my Windows stuff right now, or if I were to go program this in as a subnet mask on let me just close this real quick. If I were to go here and cd to etc sysconfig network -scripts, and then I just more my if cfg-eth 0, you would see that it's 192.168.11.245. That's my address here. That's my host address. And my net mask is the same one we just did. 255, 255, 255, 0 with some gateway, right? And then that, when we go look at it, that's exactly what we have here, 255, 255, 255, 0, which means that we have a network, a big network over here of 0 to 255 with usable hosts, and we'll talk about why we can't use the 0 and the 255. It's 1 to 254 are the usable hosts. And you say, why can't you have 0? Well, 0 is the network identifier, so that one gets tossed out. And 255 is the yelling. I want to yell at everybody, and that's going to be that way. All right. So we touched that, we touched that. We'll do the hosts and the subnets here, these equations on the next set of slides. But let's go through it. I also left all these so that if you have to do any calculations up here, you don't have to go write them all out. I did the first 16 for you, which will help us with pretty much anything we might want to do. All right, so we understand a quick binary rundown. This was quick. This was about as quick as I could do it, but hopefully that showed you how decimal works, because you've probably used decimal your whole life, and that was easy. But then we compared that to binary, and that probably was real easy to then see. And then we converted between them, and this is a thing that, again, you know, I'm not going to be, I'm not going to be like one of your teachers when you were a kid and say, you're never going to have you're never going to have an IP subnet calculator in the real world, and you're like, I'm always going to have my phone on me, so I'm pretty sure I will. That's not the point. The point is, can you understand these things so that you can pull the proper size network that you need from an IP address management tool? Yeah, there's tools out there that do all this crap for you, but you still have to know what you want, and you still have to know how to ask that. So all right, so that part's done, but don't worry, we're going to come back. So if that was rough in your head, we'll go and we'll come back and we'll do some more of it. All right, so why do we subnet? In that example we just had, we were given a network address of 192.168.1.0. With the /24, that means that the 192.168.1 is the network portion. We cannot change that. That might as well be set in stone, written on granite tablets and given to us. The only thing we're allowed to do is use the 0 to 255 in this last octet. That's the only thing we're allowed to do. They're called octets because there's 8 bits in each. Again, the 0 gets thrown away because it represents the address space. And the 255 gets thrown away because it's how we yell at each other. So I want you to look at this real quick, and then I want you to think, hey, me and 4 other college professors, we want to get in this big room here, and we all want to have our classes. I want to have my class over here, and somebody wants to have their class over here, and somebody over here, and here, and here, and we're going to just be all over in this classroom. And then when I start yelling, everybody hears it. Everybody in my network hears me yelling, everybody in this classroom. And then when another professor starts yelling, it goes to everybody. In the networking world, we call that the broadcast domain. So we want to carve these broadcast domains down, but we're not dealing with a room that actually exists. We're dealing with a mathematical construct of an address range based on how many bits we can place in those 8, well in this case 8 usable hosts that I have, right? So what we can do is we can borrow bits. And when we borrow bits off of this, we're going to take one of these that we had earlier. So these were all host bits. We're going to borrow one, and we're going to turn it into a subnet bit. Basically, we're going to cause it to be hardened down as a network bit that we can no longer change. And then it's going to subdivide our networks that we originally have. And it's going to look like this when it happens. We're going to go to a /25. So we're going to borrow 1 bit. When we borrow that 1 bit, we now have a 0 or a 1 in that far left 128th column from earlier. That's going to cause 2 networks to exist. It's almost like we put one of those big dividers up in one of those like big ballrooms or something. If any of you guys have ever been like in a convention center and they can pull the walls out and split the rooms. And in those rooms, now, in this case, the 0 is the network identifier of the first network. And the 128 is the network identifier of the second room. Then the broadcast, so when I want to yell and talk to everybody, that's the 127 over here in the first room. So I yell with 127 to hit all the hosts in here. And I yell with 255 to hit all the broadcasts of all the hosts in the second network. All right. So that makes the 2 networks exactly half the original size if we borrow 1 bit. But what if we need to carve this room up more? Well, we can actually borrow another bit. Now, once somebody in your organization, I always talk about like some senior architect or some engineer that you don't know carved this all up before you get there, because when you're a junior engineer, you're probably not going to be carving up your network. Somebody else will. But you still have to be able to look at them and go, okay, I have a /26, which means from my original 192.168.1/24 that I've carved up 4 individual networks that are between 0 and 63, 64 to 127, 128 to 191, 192 to 255. When I want to identify these 4 networks, when somebody comes and says, hey, you've got a 192.168.1.0/26, I immediately know somebody carved 2 networks off of it because I know it's a class C, and I know that /24 is what it originally was. then I can look at that and say, okay, in those columns there was a 0, 0, 0, 1, a 1, 0, and a 1, 1. We'll see that here in a little bit. And that means that 0, 64, 128, and 192 are the 4 network identifiers. Then somebody might say, and what's the broadcast address of all 4 of those? That would be 63, 127, 191, and 255. And then when college professors like to get sneaky, they'll say, what's the usable host range of the 3rd network? That would be 129, so 1 higher than the network, to 190, which is 1 less than the broadcast. That's all it is. And then maybe we borrow 1 more network. What does 1 more network look like? If we borrow 1 more bit, now we have 192.168.1.0/27. So we've got 3 network bits. And yeah, you know what, Quartz, I've been teaching this a long time, and everybody that I show this to says they like it. And that table that I use, by the way, that table's up in the Discord if anybody wants it. I'll also post the individual table if anybody wants it. I think it's the best way to work through and learn these if you want to. All right. So now look, we've got 8 networks. We've borrowed 3 bits. So in those first 3 places, it's 000, 001, 010, 011, 100. I'm not going to go through all of them, but it's 0 through 111, so 0 through 7. And in that case, on the far left. And now this is how it breaks down the networks. So I'm going to take this exact example right here, and I'm going to do this. So I just want anybody that's watching this that wants to learn this and said, hey, I got it a little bit before, but if you show me again, I'll really stick it in my head. I want you to look at this for a second, and I'm going to show you mathematically how we do this. Okay? Is that fair? Is that fair to everybody? Okay. Now I want you to do 2 other things real quick. I want you to look at and see that there's 30 hosts per network. So there's 30 hosts in here and 30 hosts in here. You say, Scott, how do you know that? Well, I can't use 0 and I can't use 31, which would have allowed me 32. So I have 1 to 30. So I want you to remember that there's 30 hosts per, and I want you to remember that there's 8 rooms. If you guys can remember that, write it down if you want. 8 rooms, 30 hosts per. All right, let's go do this again. And I ask all the questions. This is the exact. There's nothing different between these 2 slides once I explain them to you. Okay, so this one here is how we carved up the room. This is how we're going to do it mathematically, or mathemagically. But remember I said earlier, for people that got here earlier, I said everything is magic until it becomes explained to you, and then you're like, oh, that's it? That's what everybody was all, that's what people get paid a whole bunch of money as network engineers for? Yeah, this is it right here. I'm showing you. This is it. 192.168.1.0/27. Let's play all the game that we did earlier again, just for practice. 192, I'm going to squeeze it down into binary, so I have it in my hand. 128, yep, got that. 64 is left over, yep, got that. There's nothing left, so that's it. That's everything there. And I'm coming down here to look, so we'll do this one the way I normally do. 168 has a 128 in it, yes. There's 40.
When I first, so for you guys when I did this, I mean, hopefully this stuff's making sense to you guys, but this is the crux of what network engineering still is 25 years after I started doing it. So IPv4 is going away one of these days, but not yet. It's still here. So, all right, back to it. Let me know if you guys have questions. I could pause it. If you really need me to pull up one of these and just do another one for you, I can. But let's keep going. 30 is the furthest you'll go in point to point. You can't go to 31. It won't work.
Left over, which is not a 64. But there is a 32 with 8 left over, which is not a 16. But there is an 8 and an 8, so there's that. And then it's 0, 0, 0. All right. 1 is really easy. It's just this one over here. There's no 128s, no 64s, no 32s, no 16s, no 8s, no 4s, no 2s, but there is a 1. And then these are all zeros all the way out, but I'll just leave those empty for now. I know it's a class C, so this is how it was originally broken down. I always draw this first line. That's 24 network bits, 24N. And if I want to right now, I can come over here and say, well, network bits are 1s. So the hardened part of this network that cannot be changed is 192.168.1.0. And the subnet mask that I was given by default was 255.255.255.0. But somebody in my network before I got here borrowed 3 more bits. 1, 2, 3. So I'm going to draw another line like this. It's going to be a dotted line because somebody in my network carved this. Now this is still the 128s, the 64s, and the 32s place. Does everybody agree with that? But now I'm calling these subnet bits. So it's an S bit, an S bit, and an S bit. This is just what we were just looking at a second ago. Now here's our host bits. Host bits are what's left over. Okay? Now, subnet bits get 1s right here, and host bits get 0, so I go 1, 1, 1, 0, 0, 0, 0, 0. Now I got to convert this net mask back, so I got to add 128 plus 64, that's 192, plus 32 is 224. So my subnet mask for this network, somebody might ask you this question, 255, 255, 255, 224. I don't think anybody's ever going to ask you that on the street. I'm just saying, like, mathematically you might get asked this as an engineer one day, right? But now let's look at these subnets real quick. This is where you're going to go, aha, that's where he made those numbers up from. I assure you I did not make these numbers up. I'm about to do them right now. Watch. I'm going to count this. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Suffice it to say there are 8 possibilities there. And look at this real quick. The first one, if I take all the host bits and make them 0, because the host bits will always be 0 in the network address. Let's just count these up real quick. The first network is going to be the 0 network because everything will be 0. The second network, look at this place right here, is the 32 network. So the first network is 0, the second network is 32. The third network is 64 because it's right there. The fourth network is the 64 plus the 32, so that's the 96. The fifth network is the 128. The sixth network is the 128 plus 32, so the 160, right? Hold on. Then the 110 is the 192 network, and then the last one, which is all of them on, is the 224. I'm going to show you guys something. You're going to think that I have something up my sleeves. Watch this real quick. All those numbers I just said are right there. It's the 0, the 32, the 64, the 96, the 128, the 160, 192, 224. I didn't make that up, guys. I practiced it a lot, but I didn't make it up. Yeah, U-Moon, that is smooth because that's how it works. That's how it works. We're counting on these places here. So if we count, you can think of it like this real quick. You can think of it as I'm counting by 32. That's how some people like to do it. You can do this. Watch. You guys want to see some real magic that'll really fool and piss off? This is your college instructor hates you because of this one trick. I'm going to show you guys the simplest trick in all the world. If all of these bits were on, so let me show you guys. I'm going to break all these networks down. I'm going to write all the network ranges right here. I'm going to say 0 is the first one, right? And then I'm going to turn all those host bits on, and I'm going to say that's 31 because 16 plus 8 plus 4 plus 2 plus 1, if these were all on, would be the broadcast. Does everybody agree with that? Yes. But that's way too much work. I'm like Bender. I don't want to do hard work. So I'm just going to count by 32, and I'm going to say 0, 32. Then I'm going to say 64, and I'm going to go like this each time, and then I'm going to say 96, and then I'm going to go 128. And this is why I'm telling you guys that I'm super lazy, because now when I get all the way up to the top, I'm going to zipper them back, and I'm going to say, well, if this is 128, one less than that's 127. And if this is 64, that's 96, one less than that is 95. And if this is 32, one less than that's 91, this is 64, so one less than that's 63. And then if we go look at these, if you remember those real quick, and then we go back here and look at them, that was all of these ones, the 31, the 63, the 95, and the 127. It all fits. And again, like, this is well practiced. I've done this for 20, I passed my CCNA 21 years ago, and I've been doing networking for 23 now. But this is how it all works. It's never changed. This IPv4 has been exactly the same the entire time. So let's ask a couple questions there. We already know that there's 8 subnets because we can go look and count them, and we already know that there's 14 30 hosts per subnet because we looked at that earlier. But how can we figure that out mathematically from these numbers that we have here? We started with 24 network bits. Somebody carved up our network. It wasn't us. Somebody did it before we got there. And then we had so many host bits left over. It's always network bits until we subnet, and then there's subnet bits until there's host bits, and then there's host bits all the way up. They will always add up to 32. Why? Because it's an IPv4 address that has 32 bits in that address space. When we get down to the frames later, it's going to make sense that those 32 bits, you say, where are those represented? They're represented right here. Actually, I'm going to go down to them real quick. Right there. There's your source address, 32 bits, and there's your destination address, 32 bits. 32 bits across, we're looking at them right here. 32 bits across, that's them. All right, so how can we use, so I've got some equations over here. Some equations that'll help. 2 to the power of host bits you have minus 2 is going to give you how many hosts per subnet you have. Now, I told you guys I'd make this easy for you. I've got a table over here. So 2 to the power of 5 is 32 minus 2. Why are we taking 2 off? Because 0 is the network. All zeros in the host bits are the network, and all ones in the host bits are me yelling at everybody with a broadcast. So I take those 2 off, and that defines the 30 usable hosts in that range. So how many hosts per subnet? There's 30 usable. We saw them visibly, and then now we just saw them mathematically, how we count them. And then we can either count these up, 000, 001, 010, and see that there's 8, or we can know that if you've got 2 to the power of 3, 1, 2, 3, you've got the number 8, and that's how many subnets you have. So you can do this visually, or you can do this through equations, which is the way that I prefer to do it. And you might ask, like, Scott, why is this important? This right here will save you a lot of headache. This right here will help you to pass your Net Plus or your CCNA. In your CCNA, they might not ask you to break anything down, but they will show you stuff that will give you problems if you don't understand how to break where the network ended and all that kind of stuff. So, okay. I've hammered that a lot. If you guys want to do that more, let me know in Discord. I used to throw these up like challenges every now and then, and I tell you guys to figure them out and send them back to me. And if you go look in our networking topics, you'll see some of them still. But I will always use this basic template right here for any problem. It's like the movie Gladiator, where he's like, doesn't matter what comes out of that gate, if we stick together. If you stick with this model, it does not matter what IP address range you throw at me and what /subnet mask you give me. I will figure it out every single time. And that's not a challenge, but if anybody has one they want me to work on, I'll work through it and show you. But we'll do that here in a little bit, all right? And there's our Discord if anybody wants to hop down in there. We got people down there. Now, we talked about the OSI model. Let's hit some of the basics of it. There are 7 layers. It compares with the original TCP IP model that the DoD put out, but I think that the OSI model is better for teaching it. That's my mind. There's 2 primary reasons to learn the OSI model. One is to teach it and to learn it. There's this old African saying, what's the best way to eat an elephant? And the answer is 1 bite at a time. So the best way to learn this is to just take each individual little bite and figure it out. So there's 7 layers: application, presentation, session, transport, network, data link, and physical. Physical is 1, application is 7. Generally speaking, from a networking perspective, we don't care much about the top 3, just so you know. Gotta get some. Yeah, move. I appreciate you coming by. Keep working on this stuff. And again, if any of you guys want to work on this and keep this stuff fiery hot, let me know, and I'll give you examples of it on Discord. I can do that every day or every couple days if you want. Up here, we're just dealing with data. This is why a lot of times for us engineers, this isn't super interesting up here. But then when we get down to the transport layer, we take that data that's coming down and we catch it as a segment and apply a header to it. The header is one of either a TCP or a UDP header, generally speaking. There's some other things that can happen, but TCP or UDP are the 2 primary protocols that happen at the transport layer to move data around our network. We're going to get into that here in a little bit. But there's only a header applied at this layer, so we only put it at the front of the data. Then we take all of that. I should draw little lines here. Hold on. Let me get rid of all this, and I really need to show this. All of this becomes the data that goes into a packet, and the packet gets a little header written on the front of it. And that packet is going to be an IP header on the front of all the data. So all this data got squished down into this segment, and then a header was added, right? And then all of this came down and got put in here, and a header was applied. And then down here, we took all of this and squeezed it down into a frame, and we added a header, and only in a frame do we add a trailer, or some people call this a footer. It's not wrong. It's a trailer or a footer that's added. And then those all get broken down into bits as they traverse the physical network to go to the other side. So let's look at that real quick. Here is an OSI model data flow between two systems, right? This is going to be system 1 over here on the left, system 2 over here on the right. And as the data flows down from your application layer down to presentation, we're going to talk about what happens at each of these as I go through all this primer. At the transport layer, we add a header. That header talks directly to the transport layer on the other side. You can think of it as like you're writing a pen pal to your transport layer on the other side. Then the network layer puts an IP address on there, and it adds some other stuff in here that we're going to look at in a little bit. And that talks directly to the network layer on the other side as well. Then it gets packed down into a frame, and that data link, that frame sends over, and that frame is really only understandable by this side over here. So each layer talks directly across to their other layer on the other side. Everything that I show you that we do on one layer, we undo on the other layer to get back to the data that's going to be used higher than the application layer. Okay. Down at the physical layer, we simply send a flow of bits across whatever medium we're going to send it across. Again, medium is the singular of media. There is no such thing as medias unless you're talking about like multiple media, like in a American media or something like that, I guess. But media is already the plural of medium, so you don't have to add an S to it really ever. But okay, we're sending data down, we're sending stuff up. I'm going to demystify all this. Every other bit of this presentation, aside from a couple of things that outlie and stand over multiple, is going to be directly related to this flow. All right. Hey, Twisted Seed, we're doing something down in the Discord, but we're also doing it up here. People in Discord, you guys can send me messages. You can emote. I'm not really reading the Discord chat, so if I miss any of it, I apologize. But feel free to text me or send me your little womp womp and music stuff like that. That won't bug me. Actually, I think that'd be funny. But anyways, all right. So we got this, and this is going to be the flow that we look at really for the rest of this. So let's talk about some layer 7 concepts. What's happening at the top layer? Because again, remember I said earlier, as network engineers, we don't really care about what's going on here as much. This is less interesting to us. However, as systems engineers, we do care about the application layer quite a bit. And then we care about transport network, data link, and physical. Presentation and session, there's not a lot to troubleshoot there, but I'll show you guys what's going on in there, and we'll see how we can see what's going on with it. But that's going to be very, very much glossed over like pretty much everybody does. There are things to consider in these areas, but not so much with us on the engineering side of things. All right, so what's happening at layer 7? Well, at layer 7 we have HTTP. Now, you get a port with HTTP, but ports don't really come in until you're down at the transport layer, so don't worry about that too much. HTTPS is port 443 typically, and DNS is port 53. However, when we get down to the transport layer, we're also going to discuss how they can be TCP or UDP in each of these. So it might be common to think there's 65,536 ports that can be connected to on my system, 0 through 65,535. That's actually not true, because you have to double that, because there's both TCP and UDP designation of those ports. So where like DNS is port 53 and you say, is it TCP or UDP? Well, DNS is one of the few ones that actually operates on both. And by the way, if you want to test that, go to a Kubernetes cluster and only allow one or the other through a network policy. You will break your stuff. Almost swore there, but yeah, you will break your stuff really bad, because it won't work because you need both. All right. Common devices that happen at layer 7 that we care about: web application firewalls, WAFs, reverse proxies, or what are commonly referred to as load balancers. That's real big for us that want to keep like site reliability engineering, and we want to have like 7 devices back here, and we want to abstract that with a reverse proxy. We're going to look at that a little bit. And then next gen firewalls. So web application firewalls and next gen firewalls are different approaches, but they're both things that are important to understand. And they tend to fall in layer 7, although they do kind of touch a lot of the different stuff. So let's break those down a little bit. And again, you're going to see as we talk through the layers that I made this little chart. This chart is made from here, but then I just colored it on each one. Yes, I painstakingly made it for everybody. Good. All right. So proxy just means on behalf of. Almost all of you have probably used a proxy, maybe a VPN proxy or something like that. A proxy acts on behalf of someone else. That's what the word means. So you proxy out to the internet. They don't know who they're talking back to. They talk to the proxy gives it back to you. But we want to invert that. So a reverse proxy is really what we care about here. And a reverse proxy hides your back-end applications from the clients that are coming in. There's so many benefits to this. We commonly call this load balancing, because if I can take those clients and bring them in, and then they don't know where they're going on the back end, I can send them to 1 to n number of back end servers. And when I do maintenance on those servers, I can take down a certain pool of those servers and bring them back up. And with load balancers, I can do blue, green, and canary deployments and all this stuff that we talk about as engineers. I got a bunch of other talks on that. I even have some killer Coda labs that you guys can go do on those topics, right? If you want to see how a reverse proxy works to give you high availability as you deploy applications and stuff. So would a regular proxy not hide the backend IP? It does, Umoon. It does, typically. It can. Well, okay, let's put it this way. It can. In fact, if any of you guys have ever seen, there's a tool that's not really used much anymore, but it's called onion routing. Anybody here familiar with onion routing? Been around a long time. Got compromised by the government, the U.S. government, years ago. But what onion routing did at a very high level was this one proxy was actually a chain. It would be like a ring of like 100 proxies. And what would happen is you would enter that proxy somewhere. You'd get moved around through a bunch of different servers that had de-identified you. They would not keep any logs of you aside from your de-identification to be able to get back to where you came in. And then they would send you out to the internet for whatever dark web and BS you wanted to do. Then when you came back, you would come back through your de-identified chain to the one device that knew you. It would send you off, and then it would not have logs. So the onion routing was a really awesome early way that people really de-identified themselves from the internet knowing what was going on. However, probably back in, I'm going to guess this was about 2015. It may have happened earlier. I don't know exactly when it happened, and I don't do a lot with onion routing, so I don't mind telling you this. But if you think anything you do on the internet is actually de-identified anymore, you're wrong. The government, the U.S. government, infiltrated the onion routing. There's actually some white papers on this if you want to go read them, where they found out that if they could at least control 60% of this, they're all anonymized servers. You could stand up an onion router right now if you want. But they found out if they controlled 60% of Tor, it's called Tor, yeah, Tor is the onion router. They found out if they controlled 60% of the endpoints that no traffic would be de-identified to them anymore. And that's what they did. So that got compromised. That's why you don't hear a lot of those, like those activists that, Anonymous and those kind of guys that used to be real vocal and then they all shut up one day. Yeah, I don't hear anything from those guys anymore. But I'm pretty sure that they got told, like, if you don't stop, we're just going to probably just go finish you guys all off, however you want to look at that. But that was when Tor got defeated. The onion router got defeated when more than 60% of their endpoints were controlled. And you can go look. There's white papers on that stuff out there, like actual academic papers discussing how that works, if anybody's interested with that. We're more concerned with the reverse proxy. I got a question. That's why I went off on that tangent a little bit. Yeah. So reverse proxy is us de-identifying our backend from the client so the clients just come in. Oh, thank you for that, Twisted Seed. I always appreciate people giving back. Anybody that got a gifted sub, make sure you guys thank Twisted Seed. By the way, guys, I do have a challenge. Anybody, any of you guys that know me know that anything I get, I try to put back into our community. We actually have a little Code Wars challenge. We have a fair amount of programmers in the Linux community, and some guys are trying to level up. If you can beat some of our senior guys down in the in our Code Wars account, who Fisherman Guybro runs that, if you can beat like let's say our three main kind of guys, which is King Buns, Fisherman, and Sending Grounds, you'll win a like if you can beat them in Code Wars. I don't even know what that means, but if you beat them based on their definitions, I'm gonna do a what's it called? Humble bundle. I'll buy you a humble bundle. If you guys know what that is, Humble Bundle's this awesome site. Anyways, all right, I don't want to get too far afield. This is proxy servers. We're gonna go into Robedom. Go smoke them. That's what I'm telling everybody. Just go beat them. So all right. So let's talk about layer 7 firewalls real quick. I've got some images in here. I'm gonna link this up on Discord later. So if anybody wants this, you'll have all the links and stuff. But unified threat management is a defense in depth, multiple layers of security appliances that protect your system. That's typically what we mean when we talk about the term UTM. By the way, I know people come and go during a Twitch stream, so let me, real quick, I'm going to pause right here. I'm going to go back up, show you guys what we're doing. We are going through here. We're going through these topics, right? It's just a primer on Linux. The goals are for you to understand the basics, to talk about some of why we subnet. We already covered that. Talk about the flow of data through the model. We talked a little bit about that. And we're not going to become an expert. We're just surveying everything. All right. Again, this presentation will be there for you guys that want it. Proxy servers, firewalls. Web application firewalls tend to be applied by cloud providers. And then we put them in front of our different web applications. And they can be really aware of kind of what's going on with that web application. They're aware of the OWASP top 10. They can be blocking things based on like pools of IP addresses. Now that's down at layer 3, but they can do like country level blocking of things. Next generation firewalls I kind of glossed over, but they're application layer firewalls that are available. They are aware of what the application is doing. So most of you have probably worked with at least an application, or maybe you've played on like Amazon, and you've realized when you click on a certain link, there's this path that's added, like a slash cart. So now you're in shopping cart. And then you go somewhere else and it's like slash sporting goods or something. I don't know. They're mostly abstracted nowadays. But if you go to my stuff, right, it's like test and read, and it's like really basic like stuff. But my firewalls and my devices in front can be aware of the pathing that is expected. So they can look for well-formed application requests. They could know, they can be tracking and looking at that path that's coming in, and they can look at that end little path and go, you know what? This guy's walking through and they're looking for cart, they're looking for login, they're looking for admin, they're passing in credentials as, you know, you have the little ampersand to, it's question mark in HTTP, right? You can put a question mark and you can denote different fields and try to pass in strings, and these next gen firewalls can be tracking at that layer, up at layer 7, that somebody's trying to maybe message multiple times with different headers to try to log into different types of default passwords and stuff. All kinds of stuff. Yeah, sporting goods, baseball bats. Yeah, there's all these different paths that you can use. Yeah, and then King Buns is showing, yeah, age, question, yeah, they're query parameters, and they can be aware of what a good one looks like. And they can be aware of ones that look like they're trying to overload the encoding that's allowed to maybe run things on the back end. By the way, that was a huge part of how Log4j got exploited. If you guys are familiar with Log4j, what Log4j was it was a logging tool that was built into Java. I'm pretty sure. I was mostly part of the platform engineering team that discovered it and got rid of it at my old place. But you know, thousands of machines and stuff. But what would happen is people would send in these query parameters to web pages, and they would get them to execute as code in your logging system. So Log4j is doing, as your JavaScript executes and your whatever, not JavaScript, it's actual Java, is happening over on your Tomcat servers. It's logging things out, and in the logging, it would read these strings that were being passed in, and it would do executions on that server that shouldn't have been run. And then people would reset. Normally what they would try to do, there was a lot of exploits for it, but one of the most common ones was they would rewrite your etcresolve.conf if they could, to make you look as a DNS resolver somewhere out in the world. Once you can control a system like that, you can basically make a system talk to anything they want and think it's a safe communication. Like, I could make you go talk to somewhere over in, I don't know, let's say somewhere in Asia, like China or something, and make you think that you're talking to a local device in your network, right? That's a problem. All right, we're not going to get too much into that, but I'm just telling you, these are the systems that protect against that, right? And if you guys want me to do an analysis on that sometimes, there's some really good diamond intrusion analysis that have been done on those, and you can go read about them. They're all over the web. All right. Here's an example of like AWS, and you guys probably know I have a whole bunch of the AWS certs. Web application firewalls, how they work in front of your different services. So we put a web application firewall in front of like CloudFront or a Kinesis Data Firehose, and it's pulling in the logs, right? But this request coming in, we can make sure that we can have manage rules, we can have allowed things, we can block for SQL injection. I'll tell you guys one. So I used to run the web application firewall for AAA. That was something I did before I left there. And one of the things, this was actually really funny. We were getting stuff. We would always get stuff from a bunch of different insurance companies that like would sub. So AAA, some of the big insurance providers, they have independent people that run insurance, and then they will sell for the different providers. This is how a lot of people do this. Not everybody's just like a State Farm or a AAA agent. Some people shop a bunch of different agents, and they will do that via a bunch of API calls that we allow only certain companies to come in from. Well, anyways, I'm going to tell you guys about something that happened. We had one of our third-party vendors, somebody that worked for us, and I forget exactly what they were doing. I probably wouldn't tell you anyways, but I'll tell you that they were sending us a bunch of banking information, and in the banking names, right, in the banking names, I just want you guys to think about this for a second. Dust off your SQL if you don't use it a lot. In the banking names, sometimes it would be like First Select Bank of Dover, First Select Bank of, I don't know, Anchorage or something. And there was that word select in there. So as they were passing it was API bundled JSON. It was a bunch of JSON being passed in for like, authorized debitors and whatever they were authorizing against their accounts and stuff, right? But they were using the word select because First Select of whatever. That was one. Hold on. And the reason I'm mentioning SQL is probably already apparent to those of you that use SQL. But this is the name. This was in a string that was determined for the name. It looks like SQL injection. You're already, I don't have to, I only have to take you guys so far, and you're like, oh shit, that sounds really bad. What was the other one? It was SQL. So sorry, it was select, and then the other one was what was the other name that's very union. It was union, like credit unions, right? You've got unions. So select and union, those were the two major ones. It was dropping all over the place, so we had to go in and say, whoa, hold on, that's good. Yeah, well, because select is another one. If we can get you to read things, right? Select from. So it was getting stopped at SQL injection. So we had to say, no, hold on. If it's in a description field, we're okay with it from these people. So like you have to. It's almost like I tell people, when you think about security. Let's say you sold diamonds, right? You were like Jared's out here that like sells diamonds. Hey, how's it going, Gray Fox? We're just going through kind of a primer on networking. People are down in Discord. They can play music, and they can mess with me, and then we're all up here doing whatever. It was a naming convention issue. Well, Robodom, I mean, none of us know all the names of banks, right? I don't know all the names of banks in my local area, let alone anywhere in the U.S. that could be billed. So, yeah, these people were sending in these JSON. It was JSON parameters, and in the description field, sometimes it was pinging. So we had to say, hey, if it comes from these and it looks like these, then go ahead and allow it. But back to that diamond thing. If you sold diamonds, I mean, you have to open your diamond store. So aren't you always open to robberies? Yes. It's the same thing when you do anything on the web. You are open to robberies. It's you are open to attacks. My stuff gets hammered all the time. I show you guys my logs of my OpenSSH connection, but I have reasonable protection and layer security that I think is probably pretty good. Can't come in as root. You can't come in as any of the normal default users. You get locked out if you try more than 5 times. You never get unlocked, so you just get locked out forever. Even if you're some grandma that just got botted by somebody and now you attacked my network, I'm never going to let you back in. But guess what? You probably don't care anyways, right? All right, anyways, there's all these things that can happen. HTTP flood is part of just overwhelming resources. If I can't control it, nobody can have it, right? That's a denial of service of some type. Are people trying to scan and walk common paths? We can block that. IP reputation lists, and then bad bots. And bad bots, by the way, we had a really good talk a while back from my friend Jared, and he talked about good versus bad bots on his company site. And what Jared does is specifically look at all web traffic coming into $1 billion web retailer. So he looks for good and bad bot traffic, and he looks for all kinds of things, because there are good bots. There are your resellers buying things off your pages to sell to other people in real time, and you want those bots to work, but you also want to limit bad bots. So, all right, there's a bunch of other stuff going on here that doesn't really matter. They mentioned an application load balancer, which also happens at layer 7. There's other layers that load balancing can happen at in all of these systems as well, but we're not going to get into it. We don't want to get bogged down too much. What happens at layer 6? We encode things. Other layer.
If I were to inject for a second, I didn't like this was a very much a primer when I did it, you know. So I didn't talk about how the logs were coming over here and then they were being inspected in real time and then they're updating how the web application firewall works in real time against all of these different things. So there's a tremendous amount of other stuff that could be going on. Like this could be its own talk. How a web application firewall works and what you do with it. Professionally, I've used the AWS web application firewall and I've used Akamai professionally as a red team. Well, so you might say, why would the red team run web application firewall? Well, technically we shouldn't have, but there was nobody else to do it. So when I was the red team lead for AAA, I ran the WAF. Personally, I ran the WAF because we lost the two guys that they let them go. It was a mess. There's a whole story there. But after they let those guys go, then they let my manager and the director go. So I answered directly to the CISO for a while. Some of you guys were around when I did that. And then I left there and came back to just straight engineering. But yeah, that was red team stuff. And anyways, web application firewall, if you want to know more about this, the guys in our server that know this best are probably Fisherman. I think Fisherman's on right now. And also and me. We're probably the two that know this tool the best. If anybody needs time to talk about it or that kind of stuff, let us know. I'll get a talk scheduled because, you know, everybody wants to do security, but not everybody wants to dig into looking at how this stuff works. So, yeah. All right, so good. All right, let's keep going.
There's that load balancing can happen in all of these systems as well. But we're not going to get into it. We don't want to get bogged down too much. What happens at layer 6? We encode things. We decode them. So as we go down one side, we encode. On the other side, we got to decode it. You say, well, what the hell's an encoding and what's a decoding? Well, MP4 is an encoding format. And on the other side, when it comes up to be used by the application, it gets decoded back from that format, right? We compress and decompress. What are some compression formats? There's all kinds of codec streams that compress sound, especially in what we call real-time protocol and real-time sound. We compress sound. Even like, it sounds like I'm probably talking pretty fast at you, but in every second of sound of even me talking right now, there's probably like over 50% of that second that's wasted that our computer doesn't need to hear anything for that to send over and get shotgunned over via UDP to get to you. So it can compress a lot of that algorithm. It can compress that down. That's called codecs. And then we decompress on the other side by the same codec. We can encrypt and decrypt. So layer 6 is encryption and decryption of things and this is different than TLS at layer 4 or IPsec down at layer 3, right? Encryption and decryption here. I'm trying to think of some of those protocols right off. I can't think of any. But the point is, whatever you do on one side, you got to undo on the other side. Otherwise, the message isn't going to get across, okay? Layer 5 is windowing and flow control. Windowing and flow control directly affects what happens down underneath in the transport layer. Windowing is how many frames, how many segments I can send before I have to get an acknowledgement back across all of them. And flow control is how long we wait and all that kind of stuff as well, right? So there's all this stuff. Yeah, base 64 is an encoding. Yeah, absolutely. All right, so let's drop down to layer 4. Remember I said 6 and 5 we're not going to deal too much with. If you guys want to dig into that more another time, we can do that. I have to go research some of that because I haven't used a lot of that in a long time. Layer 4 protocols. There's two major protocols, TCP and UDP. There's 0 to 65.535 are the available ports, so 65.536 total can be connected to or listened to on a device that's using the TCP IP protocol stack. TCP is the transmission control protocol. UDP is the user datagram protocol. If you're going to take like a CCNA or a Net Plus, I would highly advise knowing those two very well. TCP is connection oriented. UDP is connectionless. What does that mean? UDP just shotguns data across the network. It doesn't matter if it's an order. Doesn't matter if it arrives in order. Something up higher has to deal with putting it back together. The UDP is just going to launch it across the network as fast as it can. All right? Connection oriented is going to be completely different. Oh, by the way, UDP is going to use any path it can take across the network. It does not secure a channel with the lower layer protocols. TCP does, as best it can. It's connection oriented, And there's three things that have to happen for a connection. Now, when I teach this to my college students, I'm going to tell them, I always tell them the same thing I'm about to tell you. This will help if you understand, like if any of you are sci-fi fans, or maybe if you're Pirates fans. There's Pirates of the Caribbean, which was wildly popular. There's One Piece, which is wildly popular as well. Those are pirates. There's a lot of sci-fi, right? There's a lot of stuff going on in space. But I want you to think about this for a second when we talk about like a three-way handshake and the idea that we have a connection, pass the data, and break it down. Think about a pirate ship real quick. How does a pirate take over another ship? They've got to connect. They throw their hooks. They pull them over side by side. They pass over their pirates, and then when they're done, they break apart before they loot, or they loot. Then they break apart before they burn, right? Because you always pillage first and then burn, but you don't want to burn while you're still connected to the other ship, right? So my point in saying all that is, if those happen in any other order, you don't have a very successful raid, or you don't have very successful out in space. You'd be like floating around like the Mortys that got kicked off the Citadel, right? If any of you remember that reference. So three-way handshake is the SYN, ACK, and the ACK. That is the same idea. This is the same idea as a contract negotiation. It's a SYN. I say to you, hey, I want to connect, and then you say, okay, you can connect to me as on this port and this service if you agree to these terms. That's like sending a contract to me, and I go, I agree with those terms, and I acknowledge them. Now we are in a communication. Once those three things have happened, we are in a communication. I send a SYN, you send a SYN ACK and allocate some resources, and then I do an ACK. When you send a SYN, or when I send a SYN to you and you send a SYN ACK back, we are said to be in an embryonic state of that connection. We are not yet in a fully established, what we call an established state of our TCP connection until you send that ACK back to me, or until I send that ACK back to you. Once I send a SYN, you send a SYN ACK, and I send an ACK, that is when the communication can start, and I can start to pass data in sequential order with a certain number of them before we acknowledge. We're going to look at those headers here in a second. But while this is happening, this is very important here. Great pirate metaphor. Yeah, I don't think I did it as good this time as I've done in the past, but I think that it's important. You got to send things after you've established your connection. The old SYN ACK attack, if you guys have ever heard of the SYN ACK attack, it was, I would say, hey, I want to connect, and then you would say, okay, connect, and then you would allocate some space to me. This is like a dinner party. You say, hey, I'm going to throw a dinner party, and I say, I'll be there. So you set out a plate for me. And then you send out a mass text, and I say, I'll be there. So you set out another place for me. And then I call you, and I'm like, this is Scooby-Doo, and I want another place, and then you set out a place for me, but I never acknowledge, and I never finish the connection. I just keep making you set out places until you can't support them anymore. That's the old SYN ACK attack. That's been solved greatly long ago by a couple things. Servers will only allocate so many resources before they stop allocating resources to an IP. That's important. Embryonic connections, or what we call half-open connections, tend to be limited by almost all firewalls. Almost all firewalls, like your Cisco, your old PIX firewalls before they became the ASA, the Adaptive Security Algorithm firewalls, they would only allow maybe 5 or 25 embryonic connections to any one host from any one IP, and that was just a protection. Then when we're done, we do a breakdown of the section of the session where I say fin and you say FINAC, and we're done. Okay, that's the communication of a three-way handshake. UDP doesn't do any of that. UDP is just like your crazy uncle on the back porch of a swamp, just launching his shotgun out into the night, terrified of whatever's out there, and he's just like shooting off and drinking his whiskey and all that kind of stuff. That's UDP does not care if it gets there or not. Other higher level protocols have to deal with that stuff. In fact, the question I always ask my college students when I talk about this, because we're typically on like some kind of a stream like this or whatever, is what do you guys think we're using for this? So what do you think that like a transmission like this, where we're doing video and this kind of stuff, what do you guys think is going back? It's not doing a reverse shell get around TCP. Astro Boy, everything you're doing is still doing some type of TCP or UDP. UDP is your redneck uncle. Yeah, just launching a shotgun, just shotgunning data. So UDP is typically what we're using for stuff like this, because on the telecom side of things, long ago we found out that if your ear hears a stream of data even 1/6 of a second out of order, so in 1 second, that's 1,000 milliseconds. If you receive a packet 166 milliseconds late, or at this point it's a segment still, and it's a UDP and it's 166 milliseconds behind when we needed it, you might as well chuck it out. Because if I was coming in like that, if my voice was doing that right now, none of you would be able to listen to me. I would be too jittery. I'd be like those artifact things on like the old sci-fi type stuff. Yeah, UDP is faster, and I'm going to show you why here in a second. It's faster because there's no handshake, and it's faster because there's less overhead. So let's look at that here real quick. So here's the protocol data unit diagram for TCP. This is a TCP header. So earlier when I said when you get to layer 4, when you get down to the transport layer, it's all data up here. I slap one of these bad boys on the front of all your data. So this right here gets slapped on the front of your data. There's 16 bits right here for the source port, and there's 16 bits right here for the destination port. Now, if you wanted to go challenge yourself, go to Google, type 2 16, caret is right there over the 6, you would find that that is 65,536, which is what I told you were the available source ports and destination ports. So, why is there a source port and a destination port? The source port is the port that I pick that I'm going to have you connect back to me on. So, let's say that this happened to be, you sent a request to go to the website somewhere of somebody. So I want to go to umoon.com, right? And down here in my TCP header to connect over there, the destination port would be port 80. That's the destination port for web by default. That's what your Internet Explorer, your Google Chrome, or your Firefox is going to use as destination port. And it may get redirected, but it's going to start at port 80. The source port is going to be a generally just a dynamic assigned client port on my machine that I'm going to listen back for. I'm going to listen back for port 5333. That is outside of the well-known ports. The well-known ports are 0 to 123. Those are the first ports that are well-known. And then 1024 up through like about 10,000, I think, are like the client ports that a client will normally pick. And then you have all the way up to 65,535 that you can do pretty much wherever you want. Yeah, that's Umoon. That's exactly where the port limit comes from. It's you've got 16 bits. So we could figure out the bits of whatever. Yeah, and actually, if we wanted to, we could go figure out what 80 is in this. It would be a bunch of zeros, and then we would go figure out the 80 from the last portion of it. That's all it is. Okay. So, but real quick, let's look at this real quick. Here's the RFC for it. If you want to go read the RFC, I want you to compare this header real quick with this. By the way, it's a little bit different size, but it's still 32 across. UDP has for the header a source port, a destination port, a length of all the data put together. It gives you an aggregate length of what to expect behind it, and then it gives you a checksum to be able to check if it's as long as it really is supposed to be. The checksum is the value of all the data, and then the checksum value dropped in right there, and then you strip the checksum out, you check the data, it's the right size, go on. But I just want you guys to see this real quick. Look at this. One was about this big right here, this big. But then this is the TCP compared to the UDP part. All right, so let's get that out of the way real quick. And I want to show you, these are the other things that make it. This is why we start to talk about overhead on a line. This one, again, this one's just pumping the shotgun and firing. This is like my little brotato game where I'm just launching shells at all the enemy, right? We come back here. After this, we've got a sequence number and an acknowledgement number. Now check this out. TCP must arrive in sequence order at the far side, or the far side just goes, I don't understand what's going on. It needs to be sequence number order, so the sequence will increment. When we go and we're going to look at a demo here, and if I go to any one of these TCP streams, and then I follow the TCP stream, right? So I can just right click on it and say, follow this TCP stream. Every single one of these that I walk through, I will be able to watch as I go through these, as I click through. I will see the sequence number increment and the acknowledgement number increment at the same rate as they go through. It has to. There's no other way for it to work. It's like the way I explain TCP to people when we're talking about this is like this. If a train leaves a station with 9 cars and they are in one order, there is no situation in which those 9 cars get to the other side, assuming the train takes off at full speed and goes, between here and Cincinnati, and how long does it take to get? I'm not going to ask you guys any of that. That's all basic. That's either basic algebra or calculus, based on if we're doing acceleration or not, right? Well, anyways, my point is, when it gets to the far side, it better be in the damn same order, or something happened, right? It's the same way with this. Then there's all kinds of acknowledgement and all kinds of flags that can happen in here. There's an urgency, and then there's a bunch of options, then there's some padding, and then there's the data, right? The train word problem, yeah. Road dumb, yeah, it's anytime, yeah, bad memories, any of that stuff. But I just want you guys to see that the TCP's got a lot going on. There's a lot of acknowledgement. There's the latency along the line for the acknowledgement to get back from the sequences that were sent within whatever window that you're allowed from the session layer above. So you've got a window of 18, so you can send 18 in sequence before you get that acknowledgement. If there was nothing else going on, there is, for those 18 things being sent, at least the time that the acknowledgement takes to come back, that is less time. That's less time to transmit because of the overhead of the time. Now, if we're talking like a 20 millisecond link, that's still 20 milliseconds, which is very, very short to us, but that's long to a computer. And most links over the WAN are going to be higher than that, much, much higher than that. All right. So UDP, much, much more efficient, but something higher above it has to deal with putting things in order and that kind of stuff. So there's actually going to be, I'll show a phone call with RTP, real-time transport protocol, that helps to deal with some of this, because there's other things that we can do in here. All right, other things that happen at the transport layer. And by the way, we could talk for hours and hours about any of these layers. Like, this is like, we got to talk. There's security that happens at layer 4. TLS, transport layer security. It's data in motion, right? Data's moving around. There's two things that TLS does. Two things primarily that are very important that TLS does is it verifies the authenticity of who you are. If one of you called me right now and I picked up my phone and I was like, who is this? How would I know that it was you? Do I recognize your voice from before? Have I met you? Do I know you from somewhere else? So it deals with the introduction to trust, right? So it's a trust thing, that's one. And the other thing that happens is once TLS has established that trust between us, we negotiate a symmetric key to encrypt all of our data and send the data. Now, this is not, strictly speaking, an encryption thing. We talk about encryption in other chats, and we talk about it down in Discord if people want to hang out down there. But what happens with encryption is there's asymmetric keys, where one side's a public key and one side is a private key. And asymmetric encryption costs 10 times the processing power, or 10 times the speed if you have like processing power. It's one order of magnitude greater than symmetric key encryption. What does that mean? That means if I'm wearing a little decoder ring here instead of my little rubberized wedding ring, if I was to have a decoder ring here, my system and I could talk faster like this than if I had some big sheet that was a certificate that had an algorithm that was cryptographically similar to your side, and when you sent me something, I could decrypt it only through using this other private or public key, depending on what we're dealing with, right? So TLS does those two things. It does the introductions, and then it does the negotiation of a symmetric key. By the way, the symmetric key is only used for that one run of that communication, then it breaks down forever. What I show here is the old TLS 1.2 way, which had 7 steps total, to the more efficient 1.3 handshake that it just assumes that, hey, you're a server I want to talk to. It doesn't do the hello and the hello anymore. Strip that off. All right. So with that, SSL happens at layer 7, but TLS happens at layer 4. So we're focusing on layer 4. TLS does encryption of data between two endpoints. SSL, which typically people call it SSL, but it's TLS now. Nobody should be using SSL anymore. SSL is the entropy got it. We can decrypt that too fast for it to be effective, so nobody uses SSL anymore. It's now TLS 1.3. A real quick look at that is the first part was the introduction, right? The trust. And it goes like this. I want to connect to some server, right? And I want to verify that server is who it says it is. So what I can do is I can trust a certificate authority, like CA is a very common one. GoDaddy is one that's commonly used. AWS signs their own as well. And I can pull down the publicly available version of the certificate for that server. Now the server has its private version of that certificate and that certificate key. It will never share that with anybody. But what I can do is I can send over to that server a string, and I can say, hey, go ahead and decrypt this for me. And the only person, and by the way, I encrypt that string. It's an encrypted cryptographic string based on the public key that I downloaded. And that server looks at that and goes, you sent me, Mama likes to bake cookies on Wednesday. And I say, that is what I sent you. Fantastic job. I agree that you're who you say you are. Let's negotiate a symmetric key, to just be some bullshit decoder ring. And then now our systems can, yeah, I made that up on the fly, Twist. I didn't even practice it. No, I'm just kidding. But anyways, we negotiate a symmetric key to use, and all communication, all data is transferred over that symmetric key after, okay? But they gotta send the cookies. Yeah, my mom bakes really good cookies. I can't eat them. They're too good. All right, so layer 4 example in Wireshark. So let's go look at layer 4. Here's a Wireshark capture I captured a while back, and here I can see protocols going on, and I can just go look at TCP. So when I fold this down, if you guys haven't used Wireshark before, let's see if I can zoom. I can't zoom in on it anymore. Here's the TCP information about that system. Now everything that's going on over at the right, like as I click on source port, you're seeing the hexadecimal representation. So if we were to take those 4 things that are limited right there, it's 873A. Those are hexadecimal representations of 16 bits. And you say, Scott, how the heck do you know that? Well, because every hexadecimal character is 16, it's 4 bits long. So remember earlier we looked at this here, right here? This is TCP we're looking at. The source port is 16 bits long, so it should be 4 hexadecimal bits right here. The source port is right there. The destination port is port 22, which is 0016. So we're looking at that header that was stuffed on the front of all of our data. That's what Wireshark does, in case you guys didn't know this. Then it gives us some stream index, gives us some stuff, and then the next thing it should do is go to the sequence number. Here's the sequence number. The sequence number for this is 1. This was the very first thing in the sequence, right? This is the relative sequence number. Here's the raw sequence number, right? That's some number of millions. I think it's 156,803, right? If you don't see that. Then it gives us the acknowledgement. And the acknowledgement number is also this really large number. Remember I said they're going to get really long? Very hard to control and follow these by yourself. But I can click on this, and this is one of the reasons these tools are so great, and I can follow this TCP string. So I can start at this first frame, and I can say, well, show me the second one. And here's the second one. And here's the first acknowledgement number. We're still on the first acknowledgement number. Here's the sequence number. 373 is relative. And we can just keep going through. Yeah. And we can keep walking through this for the entire conversation of this system. So if something was breaking, if something wasn't encoding or decoding right, we could go look at this. I don't think I have it on this one. Let me open up one of my other ones. Hold on. I'll open a recent one on one of my college modules here. Hold on. I'm going to remove this because I don't want this. And this is actually a call between 2 different soft phones through a private branch exchange that I had set up. And the protocol that we're using above the user datagram protocol, so it's UDP, this is a UDP, and then it's using real-time transport protocol. It's real-time. So RTP, sometimes people think it's real-time protocol. It's real-time transport protocol. They're being sneaky with the extra T. But then here's all the information about that. And then I can take this, and if it's real-time protocol, real-time transport protocol, but we're not secure real-time transport protocol, I can do something like this. And this is one of the reasons that this is so important to kind of understand this. Let's go right here to telephony and look at my voice over IP calls, and I can play this thing back. I can play your call back to you. This also is really creepy.
Hello, world.
You guys hear that?
Hello, world.
It's like the most terrifying computer voice I've ever heard saying, "Hello, world." It's fucking creepy.
Hello, world.
But anyways, that's what it is. Yeah, it's super Monka, right? So, but my point is, we can go look at this and we can see how the call went. We can see the endpoints that were involved in the call. So the source and the destination flipping back and forth. There's all this stuff that we can do. Help us. Yeah, that's terrifying, right? Okay. But this is how we capture and look at what's going on in real time in our network. And on the Linux side, a lot of times we use TCP dump, and then we drop it to a .pcap file. We extract it out of our Linux world, and we throw it into. By the way, you can still do it at a Linux desktop. I'm just saying you can pull it out and send it to your network engineers and let them look at stuff. But where I tend to have used tools like this is this happened a few years back. We were moving to a new data solution. We had a backup of all of our Linux and Windows systems, so about 5,000 machines, and I was the platform engineer over all of that. And we were going to one backup, so our backup engineers, we had a few backup engineers on the storage team, they had worked with the vendor to point all of the new agents to the new location. And then they were saying, hey, in our test environment, they got Scott, the Linux engineer, mainly, me, and then we got our network engineers on the call, because they're mostly our network guys, and they said, where is this traffic going? It is not hitting this bucket. We've got a brand new clean bucket of 0 bits over here, 0 bytes, and we want to push storage from partially to test and show, and none of the data is going over there. How do we do this? So I get on the box and I say, well, start it all up. Do a TCP dump, track where I think the data is going to go and the port numbers that I expect, and I get 0 data. So I strip off where I expect it to go and I just look for that port leaving my system. Come to find out, the vendors, and this happens, this is why we use tools like this, right? Because otherwise, I show you guys this all the time and you guys probably think I'm kidding. Otherwise, you're just like this. Like, I'm sitting here looking at a black screen, and that black screen's looking back at me, and I'm like the, you guys ever seen the, what was it, the hell's his name, Stone Age SpongeBob? And he's like, he doesn't know what the hell's going on. That's I mean, I don't know what's going on. And if I don't know how to use my tools, that's where I sit forever, right? Just, that's fucking SpongeBob. Anyways, my son used to love SpongeBob when he was little, but anyway, so we're here, and now I'm tracking and I'm seeing that it's going to the old place, and the vendor had gotten the original data and just loaded that up, and then there was some big, the time travel episode. So the vendor had mistyped in. This was a simple misconfiguration, and they were still sending it over to the other place. And now you might say, Scott, why didn't they ever catch that? Well, one, they weren't tracking over on that side systems that were already sending data in. Two, that was already a giant pool of data, so there was no way that they were going to catch that. So then we, wrote down, there's some time in there where you don't really follow SpongeBob as much, and then you get older again and it's funny again. But anyway, so we pointed it to the right place and all the data flowed and everything worked. But we fixed that because we understood the traffic patterns and the port numbers. And when we say we, I don't just mean me, the networking team and the storage team. We went in there and we found out that at the end of the day, it was just somebody had put the wrong data in. They had put the right data if we were still going to be sending it to the old bucket, but we weren't sending it to the old bucket. We were getting to a new bucket, and sometimes that's what it takes to fix. And they were like, oh, sorry, we had these email chains, and that's where I went and pulled it from, and they just didn't realize they had sent it to the wrong one. This happens, right? But we have to figure out how are we going to read this data out and get it. All right, so there's that. So that was our layer 4 example in Wireshark. Let's talk about layer 3. Layer 3 is all about routing. Routing deals with the IP packet. The IP packet now is the thing that we're dealing with. So at network, we deal with packets. Routers do 2 things by default: path determination and packet switching. They do path determination based on their routing tables that they construct from 3 types of rules. If we're dealing with Cisco, there's 3 types of rules. There are directly connected networks, which is a trust level of 0. There are static networks, which are a trust level of 1. And then there are dynamically assigned routes that are 2 through 255 in what we call administrative distance. Administrative distance is trusted at a 0 to 255 level, 0 being the most trusted, 255 being the least trusted, right? And again, this isn't about programming Cisco devices, but that's how Cisco does it, and that's how most of the systems around the world kind of work. All right, you need to add the emote. It's called mod check. Yeah, just to make sure if mod's around. Yeah, and then access control lists, we can have logic around how we filter things down. So we do path determination and packet switching, but then we added some functionality to routers 20 plus years ago where we could then filter down what's allowed, and routers can be doing a fair amount of good logical security in your system, and then a little bit about IPsec tunneling. So there's other things that happen, but these are kind of some of the big ones. The packet level here, when we look at what's smacked on the front of all the data that's come down from before, it's almost like the header is just like slapped onto the side of a box of all the data that came down from the transport layer. So now we're at the network layer. The very first thing you'll see here is a 4-bit identifier that is almost always set to 0100. 0100, and those 4 bits tells you that it is version, so this would be the 1s, the 2s, the 4s, and the 8s column. If it's 0100, it's always IPv4. That's the version right there. Now, it could be IPv6 as well, but for now, it's IPv4. And then down here, there's some other information. There's the total length, and the reason total length is given so early is because after we get down to options and padding, we have all the data down here. All the data is past this. You don't really see it because we're just looking at the header. All that data is added up, so we know the total length of what this packet should be. There's a lot of reasons why this packet cares the total length. One of them is because at the frame layer, there's a thing called, so I want you guys to think about this. At the frame layer, we're going to have a maximum transmission unit. The maximum transmission unit is like the size of the car on the top of a train, right? So like a little car that we can pour stuff into. And the maximum transmission unit on most of your networks is probably 1500. So the maximum MTU is 1500. That's maximum transmission unit. If this packet comes down bigger than that, so this packet comes down from above, drops down in, then the maximum transmission unit of the network on the frame is 1500, and you've got a little bit at the front for a header and a little bit on the end for a trailer, then I have to cut that packet and put it into 2 frames to get it through my network. Does that make sense? Then when it gets to the other side, we got to take it and put it back together. But this is really important here. We've got a little thing right here in our flags. One of our flags is DNF, do not fragment this bit. And if we set a do not fragment on a packet that's bigger than what the maximum transmission unit of the lower layer network is, it'll break. It will not send and propagate across the network. Now, you might look at that and go, why the hell would you give me that designator? Why does that matter? Well, because sometimes we have to do that for testing, and that's a very important thing for to understand your maximum transmission unit for when we're dealing with storage area networks and when we're dealing with big storage and like storage area networks and big data type movement. Because if I expect the packets to be coming down in a format that allows them to be bigger, and then they're getting chopped up smaller in the frames, that is absolutely going to affect my throughput tremendously, the kind of speed that I can get in out, my I/O speed of my backend storage for my high performance computer, whatever environment I'm in, right? So those frags are important. They give you some other information. The time to live is decremented at every hop, and the time to live for most IPv4 packets is 16. We can set them higher, but it's set typically by default at 16. So if your packet takes more than 15 hops to get somewhere, it dies. The next device that gets it that can't decrement that number just tosses it out. So the lowered MTU one day and the connection drop. Yeah, and I can show you guys, I actually show you guys sometimes how we can test that inside of a Linux network. So if you guys want to see that sometime, just ask me down in Discord and I'll show you guys that. But I make increasingly larger packets, and then I say you're not allowed at the lower layer to fragment it, and you'll see it. It'll be ping, 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 stop. And I wrote that years ago because when you're dealing with storage way over here.
Do you guys want to see that? Do you guys want me to go show you that real quick? Hold on. So let me show you guys what I mean by that, because I said, you know, I wasn't necessarily going to do it, but let me show you guys real quick. If we do, actually, hold on, my chat should be working. Undo, and redo that. Okay, you guys should be able to see me talking here. Yep, okay. Let me pull that back up. I'm going to show you guys this real quick before we go on, because maybe this is valuable to you. So, when I say ping www.google.com, we see in here that I'm pinging over and I'm using some amount of bytes of data, and I can add this. All right. Well, that wasn't on the docket. But anyways, we'll ping, and then we'll make it a bigger size, right? And the size is determined by the number of bytes we want. So if I do like 1500 here, and then and then google.com, this will ping over there. Now Google doesn't allow you to do weird stuff, so we're gonna switch to like Yahoo. Once you start messing with Google, they don't accept things back. But I'll show you right here. So I can send 1500, right? But if I were to then take this and add a -M do, which is to set the do not fragment bit on the header, it'll tell me the message is too long. We can't ping because the maximum transmission unit of your line is 1500. So then I say, okay, well, what if I go like 1460? And that works just fine because there's a little bit of additional overhead. But when you get to about 14, I think 68 is maybe the biggest you can do. And you could walk this, or you could test this. Let's go 75. Too long. So 72. That works. How about 74? Too long. 73. Yep, so 72 is the longest we can do, right? Because then there's header information in there, but we're butting up against it, and we're specifically saying you may not chop this packet as it goes down. And the reason this is so important is, you know, I used to work in data centers where I didn't have a control of the network. I only had my Linux engineering and my storage and some of these other things. So what would happen is, you know, somebody would assure me that I had jumbo frames the entire way to my storage, and then I would go test this. And I would see that, no, in fact, I do not have jumbo frames the entire way. I have jumbo frames to this device if I knew the devices in between. And if I didn't, like if there were layer 2 devices in between and I couldn't ping them, and again, I don't have maybe admin access to those switches, that might be something I have to go handle myself, right? But this is this. So, all right. There we go. Also, you know, I'll solve that later, but solve that problem later. All right. Yeah, those are bytes. Those are actually in bytes right there. All right. We're going to go back to our video. Keep watching. I can't talk too much today, guys. My voice is shot.
You've got these links in between, and your network team is assuring you that you've got jumbo frames. So the frames down at layer 2 are jumbo sized, meaning they can be 9,000 maximum transmission unit or 18,000 in some cases. And I'm saying I'm not getting that. Something's slowed down on my network. So then I would write that to figure out, and I would say it's a 9,000. I would make it a 9,000 byte packet, and I would send it, and I say you can't fragment it. And if it can't fragment it and it doesn't make it all the hops all the way across, that means that there's some link in there that is not set to jumbo frames. All right. And you might say, well, why doesn't every network team always just turn on all jumbo frames all the time? Well, because there's efficiencies to using a smaller frame set. It's set to one. All right. Here's the by the way, you may see these little links to the RFCs. The RFCs are all the engineering terms that are back there. IPv4 not embedded in IPv6. Why we don't use IPv4 by itself? They're not embedded. They're completely separate headers. In fact, I'm going to show you the IPv6 header in a second here. So this is the datagram for a packet with IPv4 packet, by the way. Now let's look at the header for an IPv6 packet. Similar size, but look at that address. Well, that's a big old meaty address right there. The source address is 128 bits. So if you want to go to Google and put 2,128, you're going to get a real big number. In fact, it's such a big number they have to express it in scientific notation. to even show it on the Google screen, right? It's something like 314 trillion times 314 trillion times another few trillion. It's some huge number, and that number is so big that this number right here, 32-bit addresses, is about 4.3 billion is about what this equals. This equals somewhere around a little bit more than all the atoms in the known universe. This is a huge number. We should never run out of it, with a little asterisk, because we've been saying that forever, right? Okay. So why do we go from IPv4 to IPv6? Well, obviously we're not going to run out of spaces. It is truly geolocation set, so all the locations on Earth are already set, and typically, probably when we get into moving into space, we'll have all those set as well, because we can easily do that. There's security built into it. I've mentioned this a few times. I don't know if I mentioned it today yet, but IPv4 was designed in a time when we were and it was still in the Cold War with Russia, right? We may argue that there is still a Cold War, but like the official Cold War, like the historically recognized Cold War. And we believed in mutually assured destruction, meaning we were going to kill them with nukes and they were going to kill us with nukes, and it was going to be terrible. But IPv4 was designed to still work even if 60% of the nodes in the links were down. Traffic will still flow with an IPv4 network, even if 60% of the nodes got cut off by a tragic world war, right? But there was no consideration in here for security, none, not even a little bit. Everything for security has been added over the last 40 years, right? So, in an IPv6, we have, and I'm not showing it here, we can go into that in another stream, or if you guys want to talk about it. After we get past this, we've got options down here, and the options allow us to add what we call extensible security. So we can add more functionality of security into this basic frame that's given right here. Did IPv6 not come about because we had too many devices and connection ports for IPv4? Yeah, so, yeah, Astro Boy, yeah, we're at 4.3 billion, but I was saying this earlier, don't we have like 8 billion people on the planet, and don't probably over half of them have phones, and all those phones need IP addresses? Absolutely. But we used a tool, we did the IANA, which is IANA, Internet Addressing Number Authority, or something like that, Internet something numbering authority, went ahead and said, hey, these are going to be non-routable address spaces that you can use only internally. So we got these classless interdomain routing internal addresses that we could all use. So I can have 192.168.1 dot whatever, and you guys could all have that, and those will never go out on the network. So all of these back-end networks share the same IP address ranges that get natted out as they leave the network. In fact, I didn't even talk too much about NAT here. I probably should have that. Maybe in a new iteration of this. But all right, let's keep going because I got to get through this. So we got that. And then at layer 3, we have firewalls, right? Firewalls also can exist at higher layers as well, but there's a little bit of a history here. The firewalls come from this older device called the PIX, the Packet Internetworking Exchange. Cisco used to call their firewalls PIX firewalls before they became the adaptive security algorithm firewalls. At the end of the day, most firewalls represent the connection between different autonomous systems, right? So we almost always have a trusted side over here and an untrusted side. I'll show that here in a second. And when we do that, we need to understand the difference between a stateful and a stateless packet inspection system. This is very important. Stateful means if I, internal to my network here, try to connect out to Google on port 80, and say I'll listen back on 5,333 over on my side with my source port, my firewall hears that, my stateful packet inspection firewall hears that, and when that traffic comes back in from Google, that would normally not be allowed back. But it sees that port 5,333 is something that I'm listening for in that stateful, it's kept the state of the link. It says, yeah, I'll allow that back. That's a reflexive access control list. It's reflexive, it's stateful, and the trusted internal can send out and get data back only from the right place. But it relies on a trust model. So we've got a trusted internal, untrusted outside. We call it reflective access control list technology because it punches a hole only allowed for that one to come back in. That, and back in the old days we gave out massive IP. That is true as well. Some companies got 16 million IPv4 addresses that probably shouldn't have had them. And then there was hoarding, and then there was selling of them as well. and renting of them too. And there's that. Stateless is different. Stateless. So the way I always explain stateful is almost like if this was like I was at a like a bar or something or a club, and I got a little armband, and then when I walk out, the armband lets them know that I can come back in. But if you guys have ever been at a nightclub where you walk out and you don't have that, now they have to check you as you come back in every time. They got to make sure you're 21 again. In the U.S., they got to make sure you're 21 again. I realize in other parts of the world they don't have that. But stateless means every packet is evaluated both times regardless. This is how we do access control lists. Access control lists are stateless. They do not care where you came from. They do not care where you're going. They're going to follow you down your list of rules every single time, no matter what. All right, so let's look at that real quick. We're in the network layer still. Access control lists. Routers have two major functions: path determination and packet switching. When they're doing their packet switching, both inbound or outbound on their interfaces, they can apply access control lists. Your access control list can be based on all of these things. There's two primary, if you're a Cisco person, there's two types of access control lists that matter. There's your source IP for there's a standard access control list, which is the basic one, and that is typically just based on source IP. That's the only thing it can do. And then there's extended access control lists, which can be based on source IP, destination IP, TCP or UDP port number, which again is up at layer 4, but they can be aware of it. The transport layer, so this is if they're TCP or UDP, and then down here is, are they some number between 0 and 65,535 for either TCP or UDP. So they can be real granular. And at network layer, they can be blocking IP or ICMP. By the way, what's ICMP? That's the Internet Control Messaging Protocol. If you've ever pinged, ping is the Packet Internetworking Groper. Ping is a subset of ICMP, and ICMP is the ability to send all kinds of information about your network and map networks. Now it makes sense that I would probably not allow ICMP from outside into my network, right? Most of your Windows devices don't allow ICMP by default with just their basic configuration. Most Linux devices, though, by contrast, are allowed to respond to any kind of ping that comes to them. So you kind of got to think about how you want to deal with that. All right, so let's talk about some access control lists. I call the access control list the coin sorter problem, and then I put a little thing down there. Only I call it that. Nobody else in all the world does. Let me see. Hold on. Let me go check. Make sure I'm not missing. I'm probably missing all kinds of stuff in here. Okay. In the Discord chat, you guys still have the ability to send me music if you need, right? Or send me whatever. So there's an IP access list here, and it's going to be applied sequentially, or procedurally is another way to say it. And it comes from the top down apply. And I want you guys to think about this. So think about a coin sorter. If I wanted to sort coins, and as I say that, I don't have a single coin on my desk, but does everybody here know what a coin looks like? It's a little circular piece of metal thing, and they're small sometimes, all the way to really big. This is the types of coins that are out there. Well, in the U.S., the biggest coin is, I believe, the $50 piece, or the dollar piece, whatever that is. That's a big one, right? And maybe 50-cent piece is pretty big. And then the smallest typically is the dime, and the dime is about the same size as a Canadian penny as well, right? And I just want you to think about this. If you were sorting coins, and the very first thing you sorted for was this big one over here, wouldn't everything fall into that? Wouldn't everything fall into that? I mean, wouldn't that be a problem for your sorting? You would come out at the end of the day and say, hey, yeah, that was really interesting. You know, I had 10,000 coins and every single one of them was a 50-cent piece. I'd be like, man, you effed up. You have to search for the smallest one first and get that one out and count that separately than those other ones that make it all the way down past your chain. The reason I say that is because procedurally what happens here as we step down through, you're either going to get allowed or denied. These first two are deny, and then we use the terminology permit, right? And if we deny you here from this source to any destination, so we just block this source exactly, then if you hit this rule, you're out. You're done. You don't get to do any of these other rules. You're out. You're done. But maybe this one doesn't apply to you, so now you come down here. And maybe this one doesn't apply to you, so you get down here. And the permit applies, so this matches, you're from this source and you're going to this destination exactly, and I go ahead and let you go over there. Now once that happens, you don't have to pass any of these other ones. You leave the execution of this logic. But I want to show you guys, if you start denying and it doesn't apply, and then you permit, and then you deny, and then you permit, but you don't meet any of these rules, there is an implicit deny at the end of all access control lists that says, hey, you made it to the end, buddy. Better luck next time. You're not getting through. Now, the way you invert this to not do that is to do what they did right here, where this allows any IP. So I deny what I want, permit something, I deny some more. Then I get here and I say, I'm going to allow any IP packet from anywhere to anywhere, and it's never going to get to an implicit deny. If you weren't denied here, I'm allowing you here. Meaning that this network right here is a pretty permissive security model. This really wouldn't fly nowadays. It probably flew about 20 years ago, but doesn't really fly much anymore. But my point is, you hit rules sequentially, procedurally from the top down. When you meet something, you leave execution. You do not have to apply to any of the other ones. This also, since we're dealing with finite systems, is why we want to be efficient with our logic. We want to hit things that are very common first. We don't want to be hitting common things as like the 34th thing down a list. That's really bad. That's all this wasted processing every time, for maybe we could logically align it a little bit differently. All right. This is the same exact thing. Once you know that, it's the same exact thing up in the cloud. So this is an AWS one. This is your inbound rules of your network ACLs, what they call NACLs sometimes. These are your inbound rules applied against the subnet right here. They're applied in order. We allow, in my network, I'm going to allow all ICMP from anywhere. And this is an inbound rule, not an outbound rule, so this is only inbound. I allow all ICMP. So I want you guys to think about this. If I allow all ICMP, which is ping, into my network, and I'm down here, and I make a rule that denies ICMP from a certain range, it's already in my network here. Does that make sense? There's no denying something after you allowed it all. So you really got to think through your logic as you build these. Then I allow port 80 in everywhere. I allow HTTPS in from everywhere, and I allow SSH in from everywhere. This rule right here will get you pinged big time. They typically don't want you to allow SSH, which is port 22 for Linux boxes, or 3389, which is RDP for Windows boxes in, right? This is always going to get flagged right here. But if I change the source to only be the network range of my externally NATable enterprise environment, that is considered a little more secure, and that's not going to hit you. But any of these remote protocols that allow everything is automatically going to get flagged. Then I got a custom TCP rule that says 124 to 65.535 is allowed back through, and I say, what the hell is that? Why would I allow all of those? Well, hold on, I want you guys to think about something. Let's put two things together real quick. Let's go back here, and I said that a stateless thing has to evaluate the packet every time. I said earlier with stateful, like at home with my stateless packet inspection, or my stateful packet inspection, that I can go out on port 80, so my machine can go out on port 80. I pick an internal client port of 5,333. It's a common one. It's outside of the 1024, the 0 through 1023 well-known ports, and I can allow it back. Well, network access control lists don't play none of that. They're like Big Gator, right? From that, the hell was it, Will Ferrell in that? These Big Gator don't play that. This network access control list is stateless. You can think of stateless as stupid if you want, but it's better to just think of it as stateless. But it doesn't remember what left. It has no tracking. This is only inbound. So if my inside machine went out to Google on port 80 and assigned port 5,333, it's the other guys, yeah. When Google comes to talk back to my machine, it's going to have the destination port of my machine as 5,333. Let's look at this rule. Would 5,333 fit in here to be allowed back? Yes. Yes, it would. So that is why that custom TCP rule is there. This allows your systems to connect out by the right to allow things to come back in. And then it denies everything. That's all this does. Yeah, Tomato. You could be very explicit in here around your network access control list and what you allow. All right, so layer 3 example, we can come back into Wireshark. We can look at any of these, by the way, the real-time protocol, right? And we looked at the UDP a little bit. And now we close those up and we go into our internet protocol. And we go, look, the first thing I told you, it's going to be 0100, which is over there in hexadecimal, that's the number 45, right? Should just be the number 4. Maybe it's just picking both of those because there's a clean one after. And then here's the header length. Here's the services, the total length of it, the identification. Then there's flags. Look, remember I said there's a don't fragment bit? The don't fragment bit is set on this packet. So the real-time protocol and the UDP that this is sent under, the packet that got generated is set to don't fragment, meaning when this got down to an Ethernet frame, it had to fit in one frame. It could not be fragmented down. So this had to fit it all in one frame, okay? Because that's set. If it came to where it got down there and it had to fragment it, it would just drop it. Wouldn't be usable anymore. So this is a look at all of those things. Here's my time to live 64, so I have 63 more hops. The protocol of the upper header is UDP, so the IP layer knows that it's going to hand up to UDP when it gets to the far side, and it's going to walk through all these things. It's got a header checksum, it's got a source address, which is a source IP of where it came from, and the destination IP address of where it's going. Okay? And then it's got all the data behind it. All right. Let's come down here. And layer 2 concepts. There's switching happening here. There's hardware physical addressing, which is that MAC address, which is 48 bits long. First 24 bits are the vendor ID. The last 24 bits are the product-specific individual thing. Address resolution protocol. How does my system know the mapping of local hardware addresses to IP addresses? Then we get to this problem of redundancy. So I'm going to talk about the fact that switching works great, but switching has no hierarchy. If everybody here moved around, your first name would not change. Your hardware name is like your first name. But if you moved houses, your logical address of how to get to your house would change because you physically moved. But your name would not change. Your name is hard physical address to you, so that's important to know. So that causes a problem because it's non-hierarchical. So once we start to add loops to our switching for redundancy, we cause a problem that is solved by a tool called spanning tree protocol. Spanning tree protocol uses this guy's algorithm. His name was like Digitskraz. I can never say his name right. But he had this spanning tree protocol that allows us to move everything towards one direction in a network. Then we've got VLANs down here. VLANs are 802.1q tagging. So we add this little tag, and the tag can be between 0 and 4096, 4095, 0 to 4095. But we only use 1 through 4094. And those VLANs allow us to break up those big broadcast domains that we saw earlier and do that within the same switching device. Then, this is important to know, once you implement VLANs, those pieces of traffic no longer talk at layer 2 anymore. You will never talk directly from a device to another device on the network in a different VLAN unless there's a router involved. It does not happen anymore. Because only the router strips the frame completely off and puts a new frame with the new 802.1q tag on there. And not that this is really about the low-level tagging, but the way that a switch blocks it is a switch looks at the 802.1q frame, and it looks at the tagging of the port, if the port is in access mode or trunking mode. And then it looks at the allowed VLANs on that port, and if the VLAN, if the 802.1q tag doesn't match anything of one, if it's an access port, or any of the many from the trunking port, it will not send it out that port. That's how switches do it. That's about all you need to know probably for most people. You probably don't need to delve down into that much more unless you want to be like a network engineer, but that's what you need to know about it at a high level. So here's the way that the frame works. The frame takes all the data. This data is the IP header and all of the IP header data, and all that data is squished down into here. There's a preamble, which is 8 bytes long. The reason the preamble exists is because that used to be the part that would have collisions in older collision-based networks. We don't have collision-based networks anymore with switches because we have full duplex communication, so we don't really do that anymore. But that used to be why the preamble was there. Then we have the destination address, which is 6 bytes or 48 total bits. 6 times 8, right? 48. Then we got the source address, where it's coming from. And then we've got the type field, which is 2 bytes and all the data. This is up to a maximum, an MTU of 1500 total. And then 4 bytes over here of the frame check sequence. The frame check sequence takes all of this and adds it up and turns it into a little checksum value that can sit in there and can be checked at each hop along the switching path to make sure that it's good. There's different types of switching that we're not going to get into now. There's there's store and forward that looks at everything every time and does the frame check every time. There's fragment free, and there's cut through, and they all have different layers of things. I don't like the term trunk when referring to VLANs, as it is an industry standard term, and the way Cisco uses it versus everyone else leads to confusion. Yeah, that's probably fair, although the other usage of trunk I didn't hear until much later. I had always heard Cisco use it for VLANs before that. But yeah, you're right. Typically, so a lot of times people think of trunks as like link aggregations, like where we're going across places, and we'll talk a little bit about link aggregation, but I'm not going to get too much into that. At least I think that's what you're probably talking about, but maybe I'm not. So here's switch management, right? How do we make switches more fault tolerant? So when we have these switches, if we just had this, and I took this real quick, and let's just clear this all off. If I got rid of these guys real quick, if these guys weren't here, this is a happy little network. There's no problems on this network. But we have what's called SPOFs. Does anybody know what a SPOF is? This is actually, I'm not being sneaky, this is an engineering term. What's a SPOF? Anybody know? It's like this. Oops. Go back to here real quick. S-P-O-F. The engineering term. It's got nothing to do with networking. It's a single point of failure. Look real quick. If this fails, did we just lose the network? Yes. If this fails, did we just lose the network? Yes. If this fails, did we? So if I just start cutting these off, look, this is a single point of failure on this network. This is a single point of failure. This is a single point of failure. As is this. As is this. As is this. This is terrible. This is absolutely terrible. This is a terrible way to live between two networks. So what we did was we said, I don't like that. I'm going to go ahead and add some switching here. But what immediately happened, because these devices, so you know, this is Scott over here and Robodom, and then this is one of you other guys over here, and I want to talk to Robodom, so I come down here and I talk here, good, but I want to talk to this person over here, and switch A goes, well, I know how to get to him, I can send him to switch B, and switch B goes, well, I know how to get to him, I can send him to F or D, so I'll send it to D, and then D goes, well, I know how to get to him, but I've seen his frame, his address come in from over here, so I'll send it over here, and then you get into a switching loop. There's switching loops where it just spins forever because there's no hierarchy to the name. There's zero hierarchy to the naming. So we had to figure out a way to cause all the data. It's almost like if you've ever held water on a plate. You guys ever done dishes and you like just let some water fill up on a plate? Then you go like this and the surface tension breaks and all the water flows one direction. That's how I think of spanning tree protocol. That's how I explain it. We're going to elect one of these as the root bridge in this network. Once we elect one of these as the root bridge, all data is going to flow towards it. We're going to turn off ports so that the data wants to flow one direction. Hey, Quartz One, thanks for the gifted subs. Anybody that got one, make sure you tell them thank you. I always appreciate it. That kind of stuff keeps me motivated. It's not why I do it, but it is kind of fun to get bits and that kind of stuff. I always appreciate you guys coming by and dropping stuff in. But look, there's no logical hierarchy. So how does this work? Again, I'm not trying to turn you guys into network engineers. I'm just showing you how it works, right? So right here, spanning tree protocol works like this. They pass around all the switches when they come up. They are not converged yet. Convergence is a very important term. I can't believe I waited this long to say that. Man, somebody needs to like put this in as like a Scott talked for 2 hours and 9 minutes and he did not mention convergence. Convergence is when all the devices in the network see the network topology the same way. All right, that's what convergence is. So before convergence, they pass around BPDUs, bridge protocol data units. They use this to elect a root bridge and then calculate which root ports flow all the traffic that way. I'm going to show this visibly in a second here, but we elect one root bridge, we use a process for that, and we can administratively set that if we want to. We elect root ports and we send all the data one direction, all right? There's a 4-step process. They send bids around, they figure out which one's the lowest, and then they all agree that that's the way it's gonna go. It's kind of like an Ent moot. You guys ever seen, remember the Lord of the Rings, or if you ever read it, the Ents take a long time to say anything? Well, spanning tree protocol takes about 90 seconds to converge a network. And I want you to think about that. That was acceptable 20 years ago, but could any of you right now imagine if you brought up your network at work from a cold state you start bringing devices up, and it took some of them 90 seconds to get going, your management would probably flip on you. 90 seconds is all fucking year for a bunch of computers, right? That's like 1,000 years for the computers. So for us, it's pretty fast, but spanning tree protocol can take about 90 seconds to converge. And the reason is because the ports come up, and there's 5 total port states, 4 of which are called transition port states. Disabled is down, so you don't transition out. But you do come up blocking, then you listen, then you learn, and then you forward out the way that you're expected to go from then on. Forwarding is where we want to be when we're all in a forwarding state, or blocking if we're stopping certain ports. This is going to make a lot of sense when you see this visually if you've never heard of this before. Disabled means I've just done a no-shut on it, or it was never configured to be up. But we block, we listen, we learn, and we forward. It takes about 90 seconds for a network to be good. Well, what if it, so this is what that old thing looks like now. By the way, spanning tree protocol is defined by IEEE 802.1d. And if you guys ever wonder where the 802 comes from, this is going to blow some of your minds. It is February of 1980 when they first convened the IEEE for the purposes of defining network protocols. So 802, if you ever wondered like where they came up with that name, it is February of 1980. That's older than me. I was born in 81. And then 1D is the subprotocol, okay? So now we've elected a root bridge. These are going to forward, and as you look at this, they're all going to send from their root port to the designated ports, and all the data is going to flow one way, or it's going to flow out the other way. Data can no longer loop in this network. Can't do it anymore. If something changes, if one of these dies and goes down, bridge protocol data units flood everywhere. They re-elect a root bridge, and then they will then be able to send with the new topology without any problems, aside from those 90 seconds, which is 90 seconds are an eternity. If any of you have ever worked in anything that's like uptime related, 90 seconds is a long time. To achieve 5 nines, you can only have 5 minutes of downtime in a year. So 90 seconds would be taking a fifth of that. Oh wait, it would be taking more than a fifth of it, because I'm thinking 5 minutes. Yeah, that would be taking that would be like a third of it almost, right? Isn't it? Yeah, that'd be terrible, right? So spanning tree protocol is good, but now there's newer versions. Rapid spanning tree protocol. Oh, I didn't align that. Rapid spanning tree protocol can converge in about 6 seconds. That's way better. Rapid spanning tree protocol comes up and it just starts. It actually avoids. Oh, dude, did they just go learn? I forget. You'd have to look that up. I don't do all that very much anymore. Then there's trill. There's shortest path bridging. There's other things that can also help you to keep these loops from happening. And by the way, I'm not even talking about the fact that there's layer 3 switches that are doing mostly IP, but they can also do switching level functions on them as well. The difference, by the way, between a router and a layer 3 switch is dependent on whether or not the path determination and packet switching is happening in software for a router or in hardware for a switch. That's the determination of that typically. Yeah, and if you got a gift sub, that's awesome, especially if it got you talking. I love when people are in here talking. That's always useful. All right, let's just talk about some various switch port topics that are important. Switches exist in typically, well, switches can be in all 3 areas, but they're typically going to be in, man, I can't believe I didn't show this. Cisco has a 3-tier hierarchy called the access, the distribution, and the core layer. Those are the 3 layers. Access is the end to all the way to the end user. Access is typically defined by port density. So our switches there have like 48 or 64 or a bunch of ports, so that we can have them connected into the horizontal cabling that goes out to our individual users out in our area, right? The distribution layer switching is typically what you would see with this. This would probably be at the distribution layer. This one here that has a bunch of like devices connected off of it, that's going to be access layer. Well, your access layer devices tend to be set to switch port mode access, and when you're in switch port mode access, you are typically only assigned one. I'll move it over here so you guys can see it with my little background there. You are assigned only one VLAN. So 802.1q tagging is only allowing one VLAN because you only have one device, or presumably 1 or 2, because sometimes you can have your data and your voice and your media, on that. But then up at your distribution layer where you've got those links going around, you typically have what's more of like a trunking. And I get that trunking is kind of a thing, but the trunking ports tend to mean, in the Cisco world, that we are allowing multiple VLANs to span that. And when we allow those VLANs to talk between the two different switches or multiple different switches, we have now caused those VLANs to exist across all of that. If you have VLANs on, I explain this to people, if you have VLANs over here on a switch, you're using 1, 2, 3, 4, and 5, and over here you're using VLANs 1, 2, 3, 4, and 5, and you do not trunk between those, you have 5 VLANs over here and 5 different VLANs over here. They are not the same. But once you allow trunking, in Cisco terms, to connect, then all of those are the same VLAN and traffic will flow across them that way. OSPF is a routing protocol allowing you to connect one network to another. Yeah, I didn't even get into routing protocols here because, man, I could talk for a long time about routing protocols, but I definitely didn't want to blow people's minds up. So what actually is a VLAN? So what a VLAN is within this frame. Do I have a frame here? Yeah, within this frame, we add up here, there's actually a little thing that gets added. I didn't even include this, but I should have included it. We add a little tag for 802.1q. It's a, how many bytes would that be? I think it's 8 bytes. 10, I think maybe a 10 byte. No, it's got to be big enough to do 4096. Somebody do that math for me. And then when that tag is applied there, our switches will no longer forward anything out a port that doesn't have that tag on it. So what it does is it causes our networks to be a virtual local area network. So only devices that have that tag talk to each other down in our layer 2. Then you say, well, so you shut off all these other ones from being able to be talked to, and I say yes. And you say, well, then how do I, over here on the accounting team, talk to my servers over here that are in a different virtual local area network? And I say, well, I'm glad you asked that. You have to go to a router. That router has to assign a new frame with a new tag on it and send you out to that device so it can get over there. Yeah, so it's a virtual local area network. But it's been done at the lower layer, layer 2, where you typically have to define networks at layer 3. But you can do it virtually with a VLAN. That's all it is. Other things that can happen. You should really shut down ports that aren't being used at the access layer, and you do a no shut command to reverse it. By default, most devices have their ports off, so that's good. You should use switch port security to limit MAC addresses. You can make it learn the first MAC address and then not allow others to come in. People used to just drop wireless access points, and we call them rogue access points. And rogue wireless access points are terrible. You don't want that in a network. Switch ports can be trunked or access mode generically. Trunk means that they are forwarding VLANs to other switches. Again, that is in a Cisco context. Access means that they have one 802.1q frame tag allowed, which means there's just one VLAN on that port. And then, this is just a concept, I didn't have time to go over everything, so I'm trying to hit like a lot of it. Link aggregation groups came later for me. I did network, I passed all this stuff before link aggregation groups, and then I kind of learned these in the wild. But what link aggregation groups is when I showed this earlier, I'm showing this and it looks like it's one link everywhere, and you go, Scott, you were drawing those little X's and stuff. Yeah, but here's the thing. I can take these and I can actually have 4 links across. So let's say these are all 10 gig links. And I can take 4 links together and I can define them as a link aggregation group and say, hey, you know what? You 4 right here are connected over to that switch on those 4 there. Let's just go ahead and send all traffic over the 4 of you at 10 gigs each as though you're one link. So now you've got 40 gigs between those 2 switches instead of just having a 10 gig link, right? Now you've got 40 gig links. So link aggregation groups really opened up this world, especially like I'm in the high performance compute world where I want all the speed, give me all the speed for my Lustre and my GPFS file systems and stuff. And I'm already dealing with InfiniBand most of the time. But now I can do link aggregation groups and stuff and get massive speed increases between devices and all this kind of stuff. And also highly available. Like, think about it. Who's using 40 gigs between their devices? Probably some people doing a lot of queries to SQL, probably that kind of stuff. But in your organization, would losing one of those be acceptable? I mean, having 30 gigs is surely still good for a lot of people. Oh yeah, it's degraded. Yeah, we mark it as yellow and We make sure that the NOC keeps an eye on it, and then we wait for the vendor to send us a new one and replace it and this stuff. But my point is, you're not completely down. I would rather be hobbling around than being completely knocked out, right? Like, I don't want to be down. Throughput increase, not speed. Yeah. This is true. It is a throughput. You are still technically only using the same amount of 10 gig links, and you're still only using the same amount of speed. You just have more bandwidth. That is true. Absolutely true. Okay. Layer 2 example in Wireshark, same type of thing. We come down here, and hopefully you guys have noticed that aside from the fact that I just changed the one PCAP I was looking at, I am looking at, for the real-time protocol, this real-time protocol up at layer 4 got stuffed down into an IP packet, got stuffed into an Ethernet frame, and it got all of these things on it. It got those Ethernet 2 frames added to it, and then at the end, the frames at the end of it. But my point in saying all that is, it's all going the same place, because then it goes as bits across the line. So that's the last part, is bits across the line. All right. So layer 1 concept. There's no protocol data unit here. There's no PDU. It's just bits. We're just launching bits as fast as we can from one side to the other. You're simply encoding bits onto a medium. Medium is the singular of media.
Let me say something here real quick. This is one of the parts when I did this originally that as I looked at it, I was like, man. So I probably did the least amount at layer 1 of all of this compared to what I normally do. I teach 3 different classes that go over this at the college level. I've taught many more over time, but I'm saying I have 3 active ones. Anyways, the point is, if you guys ever want to get down into the wireless and the way that this works, this won't be the one for that. This one right here is very high level, and it won't spin you off really far into this. But also, I don't think this is maybe the stuff that people find as interesting if you want to be a Linux engineer or those kind of things. So I didn't spend as much time digging into this. But if you're like talking about just straight moving bits around, I've been doing that for a long time, and this is a kind of like a hobby of mine as well, how we move data around. So, okay. Anyways, I'm going back to the video. Just don't expect the video to be that much, because it's not nearly as deep as it could be. And my video doesn't want to work. That's weird. I've never seen Media Player not start before. I don't know what is going on there. Change back over here, change back over here, and nope. Just not running. And this is off of my local machine, which is doing fine on everything else I'm tracking. So this is a new one to me. Yep, we'll give them the old maximize, minimize the player trick. Nope. We can go back here. There's Ranger stuff. Go pop back into the network primer. We'll go to 16 minutes left. Oh,
You solved the noise problem
hold on. Right here.
type of thing. We come down here, and hopefully you guys have noticed that aside from the fact that I just changed the one PCAP I was looking at, I am looking at, for the real-time protocol, this real-time protocol up at layer 4 got stuffed down into an IP packet, got stuffed into an Ethernet frame, and it got all of these things on it. It got those Ethernet 2 frames added to it, and then the at the end, the frames at the end of it. But my point in saying all that is, it's all going the same place, because then it goes as bits across the line. So that's the last part, is bits across the line. All right. So layer 1 concept. There's no protocol data unit here. There's no PDU. It's just bits. We're just launching bits as fast as we can from one side to the other. You're simply encoding bits onto a medium. Medium is the singular of media. If you learn nothing, I should have put this as, if you learn nothing else from me today. Medium is singular, media is plural, right? Bits can be sent in either analog or digital formats, depending on the type of medium you're using. Analog is a perfect continuous wave. Typically a sine wave. We can also send other types of waves, but it tends to be a sine wave. It presents a problem though. An analog perfect wave will be affected by noise in such a way that you will get spikes and jaggedness to it. It's no longer perfect, right? This is a sine wave right here. In fact, that is one oscillation of a sine wave right there. If I had this, and I said this was 1 second, that would be exactly a 1 hertz wave. Then if I erased it, and I went like this, and I said this is a second here, and I went, that is a 2 hertz wave now. 180 degree shift of a wave is 1 full cycle. So from here, actually to here, don't worry about that one. From here to here is 1 shift of the wave, and then from here back to here is 1 shift of the wave. Yeah, that's 1 oscillation of the wave. This should come up a little more. Okay, this would be a 2 hertz wave. But if we start to get noise on here, noise against our perfect continuous wave, when we go to amplify this, we amplify the noise with it as well. When we make it stronger again at the next repeater or whatever, it amplifies the noise. Now compare that with a digital signal. And we'll just assume that it's like a Manchester encoding scheme or something, and this is a 1, this is 0, and this is a 0, and this is a 1 because it's the shift, and this is a 1 here and a 1, and that's a 0, like whatever it is. If this gets some noise to it, but it's still repeatable, and it comes out on the other side, it's going to be a perfect wave again. Does that make sense? Because digital can only send a 1 or a 0. So with a analog wave, you get a continuously increasing noise problem as you go further. But with digital, you solve the noise problem every time you retransmit the signal, because it's always a crisp, clean signal again. In the 80s, if any of you were alive in the 80s, I was very young, but I remember it. Sprint used to always come on and say, "So clear you can hear a pin drop across the country." Right? So what Sprint had done was, when we talk, I am talking analog to you. It's going into my computer, and it is being changed to a digital signal, where that digital signal is then going across to my modem here. That modem is probably translating it to an analog signal to go out, get on a device, go back to digital, go over to you. But when you hear my voice, it is an analog again. It has been transferred multiple times. But as it's traversing those lines, the digital can be cleaned up over and over again. So that's actually what Sprint meant when they said, what's the noise? Does it not distort the signal in terms of 1, 0? Yeah, well, there's a tolerance. So if this is a 5 and this is a 0 voltage, right? And you got to start to get some noise that looks like this, right? And it's, it's kind of a little messed up, but it's not so much that the other side can't still see it as a 1 and a 0. Then when we transfer it back out again, it looks clean again every time. So you always get noise, but noise is wiped along a digital path. So that's kind of an interesting thing. Then we take multiple signal streams like this, and we multiplex them down into one bigger pipe channel. And multiplexing is the idea that this is like data 1, data 2, data 3, and they can all go over one channel path. Now, we can multiplex by time, by code, by frequency, by we do time, so we do time, we do code, we do what's the one in between there? I think I have it in one of these slides. And then the medium or media can be physical or through free space. Physical media is electrical or optical signals. Electrical signals are electrons flowing over a copper wire, typically copper, and can sometimes be gold, in fact. But a copper wire They are affected by friction. Electrons experience friction as they flow through an electrical cable. As we introduce more and more of those hertz, we introduce more and more heat. Optical signals are photons passing through a clear core, going out into the cladding and coming back into the core. They do not experience heat. They do not experience electromagnetic interference, but our bits do. So electrical does experience, it both creates electromagnetic interference as it moves, and it also is affected by electromagnetic interference from the environment. So it's both. Free space can be energy of electromagnetic waves or laser waveforms. Those are the major ones for that. Okay, so that's how we send data. Wait, do I have? Oh, let's go here. Here's a sample. So if we've got an analog signal and it's traversing whatever our analog signal looks like, and we downsample it at whatever time sampling interval we want, which is typically many, many thousands and tens of thousands of times a second, then on the far side, we can put that back together to analog to be able to hear it pretty crisp again. If you guys have any friends that are like, they insist that they hear stuff from like a record player because when it comes off of a digital signal, they insist that they can hear the difference, it's technically different. Because even though it was sampled a lot, it is no longer this perfect wave. It is now straight across. Now, there are people that will argue, well, the human ear, we figured out all the sound stuff by like 97, so there's not really anything else to figure out. I don't know. There's still a lot of people out there that swear up and down that they can tell the difference. So, if you guys remember the early days of like Napster and LimeWire and that kind of crap, you wanted the highest sampling rate of a song as you could because then it would be the more clear, crisp song or whatever. All right, so we downsample. How do we multiplex? Here it is. It's frequency division, multiplexing, time division, and code division. I was forgetting frequency division. We transmit 2 or more signals simultaneously over a single communication channel. We aggregate signals up. What benefits from that? Telephone systems, telemetry, satellites, broadcasting. But if you want to look at it, it's almost like this. Like you've got a frame, you've got a set of time. Like time is like a little river flowing. And as long as there's nothing in there, you can just drop something in that time. We have all kinds of different ways that we deal with who can transmit on a time division multiplexing system. We can have like a token passed around, like an old token ring network. We can have you get polled and you get to transmit during your time even if you have nothing to transmit. You can request to transmit, RTS, request to send, and then you'll get approval to send for the next X amount of milliseconds and that kind of stuff. So either way we do it, we have one channel, but we can have multiple signals because we've divided them by time. At the end of the day, this is exactly how virtual machines work against a host. The host just shares its time against processors because the host, whoever is the running kernel or the running system, owns 100% of the processor. But it shares the signals that come from the VMs down in a time division multiplexing way. It just does it pretty fast, so most of us think it looks good, but it's still time. All right, additional topics. Let's talk about some other stuff. There's a direct attached storage and network attached storage. And then when we get into those, direct attached storage is physically on the system. So strictly speaking, this isn't anything to do with the network. I just put it in there to compare it with a network attached storage, which is typically over an Ethernet connection. Could be fiber channel over Ethernet. It could be InfiniBand. However, the differentiation between a network attached storage and a SAN I'm going to go into in a second. By the way, this bugs me a lot. Like, if you're a new engineer, you got to learn it. But for people that have been doing this for a while, NASs and SANs are completely different things. And that should be known to people that have been engineering for a while in that space, if you're engineering in that space. All right. So it tends to be connected rate. Then there's different protocols. There's NFS for Linux. There's CIFS or Samba connecting into Windows. And Linux shares, letting those things talk to each other. This is important to know what protocols are there because like NFS uses port 2049. Once you have port 2049 open or not open, that's going to determine whether or not you can share NFS on your network. If NFS is not working, you might need to go check to see if there's a firewall in between your devices that are blocking. A lot of times nowadays with like zero trust models where we lock everything down, a lot of times ports are not open between devices in different subnets. So you got to go make sure that's right in your company. All right, so an important distinction. If you've got a bunch of servers sitting here, right? And over here, you've got your different clients, your network access, right? these are us sitting at our different computers. Is NFS traffic encrypted? Yeah, you can encrypt NFS traffic. Yeah, you can. It's not encrypted by default though. No, you have to encrypt it yourself. So if you're just passing NFS over the web, you might want to make sure that you encrypt it. For sure, in NFS version 4, there's a thing you should be able to encrypt that. But I just want you guys to see this. If this is the traffic right here where we're talking to our network file system and our servers here, and we're talking over NFS and Samba and AFS, maybe whatever AFS is, and we are talking over the same Ethernet network that we also do DNS queries, port 53 DNS, and all of our reverse address resolution protocol, RARP and ARP, are happening right here. And then we're also having communications between our devices for our Teams channel calls and those kind of things. This is our data, or this is our management network over here. So network attached storage is our devices are using the normal network to access things. Now if our servers have a back channel separate network that is running typically fiber channel or iSCSI, or sometimes it's InfiniBand, and it's talking directly to storage devices only, and it's pulling data over, once those things happen, that is a storage area network. But these devices do not connect out to Google over here. They do not talk Teams messages and other kind of bullshit, voice over IP and stuff. That's all happening over here. So if you have network attached storage, you're talking to things that are attached to your network. If you have a storage attached network, it is a dedicated network for storage between your devices and their back-end block devices. That's what it is. Apple filing pro. Oh, nice. I didn't know that. Yeah, I don't do anything with Apple. Not even the tiniest bit of things with Apple. In fact. All right. So storage area network again. We have jumbo frames. We have more with storage area networks. We can do more things that cause inefficiencies on small traffic, but great efficiencies in big data block transfers. So that's what happens here. Typically over there, we've got this new type of addressing that we hadn't talked about before, which is the worldwide node name. Instead of a MAC, it's a locally unique thing, yeah. And then servers typically have like a host bus adapter plugged into them instead of a network interface card. Now, your device can have a network interface card or even 10 over here and have a host bus adapter. And over here, it can be sharing NFS out for your people. And that connection is a storage, that's a network attached storage for them, because they're NFSing over and whatever. But then your device is getting its backend storage off a high-speed storage area network. They are two different things, and I really like that drawing for the distinction. All right, storage area networks can be something like this. By the way, in this example, you might say, Scott, hold on. We've got Ethernet switches and fiber channel switches, and now I see that the NICs are going over here. And how is this? Okay, so this looks like what you define. There's my NICs or my network attached storage, and then my fiber channel backend. Okay, good. But then you say, well, what about this one? Well, there's a distinction I want to make here that fiber channel over Ethernet is typically such big 40 gig or 100 gig links over fiber that we can carve that link down where 10% of the traffic is truly your management traffic, and 90% of that traffic, still over the same link, is going to a storage area network. And in that case, because there's that distinction, it is still network attached storage this way and storage area network that way. Even though you're like, but you just said if they're over the same link. Yes, however, we're carving up a very, very big pipe to get the bandwidth and throughput that we expect for our systems. All right. Do routers and switches need to support jumbo frames? They do not, pseudo, please. In my case, I typically use it for all of my big networking and that kind of stuff. Big data, like my back-end, big storage type stuff. So not all routers and switches need to support jumbo frames, no. Nope. Then a little bit of stuff that doesn't fall in anywhere, intrusion detection and intrusion prevention. What are those things? Intrusion detection looks at statistical anomaly and what we call heuristics, or it looks at signature-based detection. Signature-based detection only works if we've seen something before. Statistical anomaly looks at things that could be a problem based on like trends and old data and that kind of stuff. And statistical anomaly is only going to be as good as data you've collected before. Signature-based detection is only going to be as good as the updates of your signature database, right? IDS can be host-based, network-based, or we can do port mirroring and then listen to things, or we can have event buses nowadays that do something similar to port mirroring and that kind of stuff. Not going to get into all that. Where we go from here, I didn't even update that, so don't worry about that. If you have questions about any of this stuff, message me on Discord. If any of that stuff's interesting and you're like, hey, Scott, I want to dig into that more, or if you want, I mean, this isn't a, strictly speaking, a networking group. We're a Linux group, but I do a lot of networking. So if you want to know more about Wireshark, I think the best thing is to play with it. But the second best thing is we can go through and work on some stuff and look through it if anybody wants to do that kind of stuff. So, all right. With that, I'll probably drop the stream. I am surprised that my guys in Discord, like, can I say something to my people in Discord? You guys were remarkably well behaved for what I expected from you. I expected, like, so much of that stuff from you guys.
Ha, that's kind of funny. So let me go over here. This is my little co-working chatting stream. And let me make sure. Yeah, okay, that's the right screen to show you guys. What we could do is I have another video that we could do, or we could just be done. I'm just kind of looking for, let's see, where do I have this other one? I definitely can't spend too much time talking though, whatever we do. Let me go grab this thing. Let's see. So it's kind of interesting. Oh yeah. I'm not worried about COVID. I'm pretty sure I don't have it. I mean, this happens to me every year, and well before COVID was released. Let me go find and they don't make this easy to find the freaking video I want. It's like you would think there would just be a place to go pick a new video, but there certainly is not that. All right. So, I'm going to go jump over into this other thing that I have, which where is this? Hold on. Well, actually, I do have all the speaker videos, so if you guys had any of the videos that you wanted to see from our big event that we did back in August, I do have all of those if anybody wanted those. Well, just wanted to see them. They're all up on YouTube as well. But I go here and say HPC. All right. So this one has, go forward a little bit. This one was presented last year. Oh man, that's funny. And we'll go ahead and we'll watch this one for a little bit. If anybody's got any questions about high performance compute, this is the space I directly work in all the time. So I'll run this one. You know, if you guys have questions, you know, feel free to ask them. I'm just sitting here hanging out, and hopefully this stuff's useful to you. Huh. We're getting that same Same weird thing again. It's like it's not reading the memory or something.
Told her. So I don't know when the wife's getting home. She's hanging out with one of the nieces. We'll go pop over here.
All right, here we go.
We'll get the little Ranger cam going. Oh man, I gotta sign in and everything. Hold on. That should be Nagios admin and Nagios. Wait a minute, what happened over here? Hold on. Get over here. Ah, there I go. Now I can see anything. Hold on. Is that Nagios admin? I think. And that one's maybe that. There's Ranger. By the way, Ranger's been a little bit slow getting up the last week or so. We got him on a bunch of drugs now. On last Sunday he went on an emergency vet, and then just Friday he went on his regular vet. And man, I mean, it's not like an acute sudden onset of being old, I don't think, but he's having problems, and they think if he doesn't get better in 5 days on all the pills and stuff they got him on, they're going to do x-rays because they think he hurt his back. So, oh man.
Update, Ranger's doing a lot better now. He was faking it. Okay, that's not completely true, but Ranger's doing a lot better.
Told Ranger, I'll just do it real quick with a garrote. No, I wouldn't do that. Can't tell my wife that anyways. All right, anyways, so what are we doing today? That was a Ranger check, so Ranger check's good. We're gonna do some system stuff. Oh, I'm not even all connected. Hold on, let me connect up here real quick. Get on some of my stuff here. Hopefully I didn't drop anything here. Shouldn't have. Let's jump on this guy. Let's get on this box. So this will be a server that we'll use to kind of do some, testing in general, looking at system stuff as we go through this. But this is the HPC system engineering topic talk that I gave earlier to our prologue. And I know people wanted to see channel redeemed for upgrade one home lab. Fisherman, I used to have that, and you might be surprised, but I think I had that. Wait, can I not see my channel points? Hold on. Oh, it's 8,000, but maybe I got rid of it. Maybe I got rid of that one. It says it's 8,000 on there, but here's what we used to have in the home lab. Wait, hold on. What was this called? It was name of that board where you put the sticky notes up. Hold on. Oh, what the heck is the name of that board? You guys, I'm drawing a complete blank here. Not a Cabana board. Fuck is the name of that board where you put the messages? It's like an old project management Kanban. Yeah, so I got lab cleanup on Kanban. I don't know if you ever saw this, Fisherman, but what? I don't remember how to get in here. Maybe that. Oh yeah. I have all kinds of stuff I need to do in the lab. I just don't do it. Yeah. I got this one, and then I got the home version of this. So there's like there's the lab cleanup and the home projects. So lab cleanup's all this stuff. The home projects are all these things I got to do around the house eventually.
The M deals with the permutations and whether or not you are going to fragment or not fragment the bits. So the easiest way to find that. So I got asked a question if you guys missed it, and it was like, what's the M do? So we just clear it. We say man on ping, and we go to -M, and right here it's the select path MTU discovery strategy, and it may be to either do, prohibit fragmentation, even a local one, want, to do PMTU discovery. Fragment locally when packet is size large, or do not set the DF flag. So this is when you hit don't here, it's not don't fragment, it's don't do fragment. And when you hit do here, you're saying do prohibit fragmentation. So that's why we use the -M like that. So I think that's a question from earlier. Maybe you're catching up, but that's what that is. All right, going back to the video.
Or things that I've done, some things I've done on the far right. Anyways, AWX upgrade. Oh yeah, I've been meaning to do it for a long time. Oh yeah, you guys have been telling me to do shit for a long time on this channel. I haven't been doing it.
I still haven't done any of that.
Yeah, so I can upgrade AWX. What I need to do for AWX is like this. Let's just get in our box here. So I gotta do something that, let's get this all connected up, just so we got it. We'll put it here. So it's on the other side of this. And what I need to do to fix that up is I've got my production, what the heck? I leave it on a thing and then I find, oops. There we go. So all I need to do is come in here and just set this all up. So that's all I really need to do, and then I would just decom the old one because I think my version's on version 9 right now, and that's all I got to do to get the AWX going. I haven't done it yet. Yeah, if you fix a lab item, yeah, Fisherman, we can do that. That's not what I was going to do tonight, but I was hoping to just mess around tonight, talk about this HPC type stuff. But I got to rebuild Jumpo 1, man. I got so much crap to do on here. Pulp install, telegraph. Pi-hole, people want me to set up Pi-hole, play with Tmux. Oh, daily pull of all the IP data using Python and Folio. I've done all that before. I just need to show how to do all that. Yeah, Fisherman, I haven't looked at.
All right, I gotta jump forward on this. I don't know what the hell I was doing. That was bugging me. I'm like, what the hell? I need to re-record this, obviously.
I need to set up some security stuff. I did set up the Kubernetes. I've been doing Linux for about 20, so professionally. So, let me know if you guys have questions or you want to work through any of this. But let's go through it. So here's kind of the overview. What is HPC? How is it used? What industries and applications are you going to find it in if you're trying to get it? Professionally, yeah. In that people paid me to do it or to not do it in some cases on their systems. System skills, these are generic Linux skills. Like pretty much everybody that probably watches my channel, for sure everybody down in the professional Linux users group, are people who have some basic Linux skills. But maybe we're a little rough around the edges, maybe we're hobbyists and we need to learn it a little better. So this is my idea of like what I think you need to bring to the table and things that you kind of need to know to be able to do HPC stuff. You pick this up being just a systems admin and systems engineer and that kind of stuff. And then I get into like the nuts and bolts of how HPC works, what the compute nodes are, what the cluster management systems are, how they work, what the schedulers are, what the shared storage is, how the networking works, and then what types of HPC tooling you're going to see out there. And that's kind of my overview of this talk, right? I might not go in as much depth on this one. Just depends how much time I got. Again, I don't know exactly where the wife is, but she should be back in a little bit here. So we'll run through stuff. I try to do when I stream, I try to do at least an hour, so try to get some stuff in there. All right, so what's HPC? High performance compute. That's a term that's out there, but that kind of is like the cloud. Like, what is the cloud? The cloud's a lot of things, right? Well, the NIST has very well defined what the cloud is, but HPC, in my mind, and kind of what I've seen over the years, is it's a lot of different things to a lot of different people. You're going to get a lot of different answers. So for me, it's something that exceeds the computational needs of one system. That's a very generic idea, but it will help you to kind of spackle on everything else that's going on. Yeah, Fisherman, I think you can definitely set up a 2 VM test HPC cluster. Yeah. In fact, the one that I'm going to put in the lab looks kind of like this. It's funny, I don't have anything up. Let's pull up Excalidraw, and then let's back out a little. I'm going to be putting one in the home lab, and we'll have a login node with a Slurm scheduler. Then we'll have some compute cluster of some type, and then we'll have a management node over there that we can do like XCAP management of the systems from. So I do have a plan to set that up in the home lab. Well, a plan in that I made a drawing of it. Maybe it's not a full-on plan yet. And then I use this for a part of my drawing that shows up later when we talk about the networking and stuff. Oh yeah. If you missed the end, that's fine. But the main point of high performance compute is we're going to need more than one system to spread out a workload. You have to code your application to do checkpointing and to be able to split the workload, but there's a lot of libraries that can help you with that kind of stuff. And did I spell procedurally wrong? Where is it? Where's it at? Okay. So yeah, we got to spread things out, right? This talk is going to discuss common HPC technologies, uses, organizations. The learner, so anybody that wants to hear it, here hanging out, will be better informed how to get into the HPC space if you're in a general Linux background. So, you already know how to get your hands on a keyboard, do some of this basic stuff. Black background with green and different color letters don't scare you. That's kind of what this talk's for. However, if you hear in this next few parts when I start talking about like the system skills you need, and you're like, hey, I have those gaps and I know I need to get into there, then you can talk about start thinking about how to close those gaps and learn that stuff, and then you'd be pretty ready in that space. So okay, what isn't it for the purpose of this talk? These things are HPC adjacent. I think my doctor told me to get an HPC shot. Yeah, HPC adjacent technologies are like big data processing. So Hadoop, MapReduce, Elastic MapReduce, things like that are not directly part of HPC for the purposes of this talk. Do we work a lot of the same workloads between them? Sure, but in strictly what I've seen as HPC, high performance compute type space, that's considered something else. Just so you know, those type of workloads get run and managed and processed slightly differently. So then data lakes, data warehouses, and lake houses, there's a lot of terminology for this. All companies out there need big data. All companies out there need to store their data in a manageable, structured way so that they can query it and check it. That's what data lakes and data warehouses and lake houses are, and all those things. That is not specifically what HPC is for the purpose of this talk. Do we have huge amounts of storage, like in my case, like petabytes and exabytes tied into our HPC systems? Absolutely. But they're not doing this type of structured data that you're trying to get out of this. That's not the purpose of it. They're more like genome sequences and large data sets of weather and things that themselves, once they're processed, you don't always necessarily need the raw data in the same way you might need some of this stuff. So I just need to make sure it's a little bit different. Cubicle Jeffrey Dahmer over here. That's funny. I heard Jeffrey Dahmer reference like 2 hours ago with RoboDom and Salty, which was kind of funny. All right, so what isn't it for that? Let's put that as those are adjacent technologies for this. They're not needed for this. What type of SAN storage is currently used in HPC objects? No, actually, surprisingly, Fisherman, The two main ones that I'm going to talk about, Luster and GPFS, are file system storage. They are file system. The way the client connects is novel and faster. It's novel and much faster than a normal system. But yeah, Fisherman, it's they're going to be file level, like the same as a file share type connection. So I'll show you that here in a little bit. How's HPC used, right? Government, military. I know that sounds redundant, but when I say government here, I mean more the different government entities, and then military, I mean specifically for military applications, which are different to me, having worked with both of them. Academic, I'm heavily in the academic space. I'm currently working in an HPC environment that is all that space. Red Sly Fox 8, we have a bunch of people that are, one of our guys just was working on his CYSA. That's CompTIA, right? One of our guys was working on that as well. Yeah, big government definitely has big compute, that's for sure. And then private research sectors, all find applications. I've never worked in the private research sector. Well, actually, no, I take that back. I have. I've worked in all of these now that I think about it. Caris Life Sciences was private research. We were the biggest cancer research back in like 2015. We were the biggest cancer research repository in the world. And we almost got bought by Google like twice while I worked there. It was kind of wild. Never saw any aliens, no. But medical industry, like, protein sequencing, protein folding, those kind of applications, genomic applications, so looking at the human genome, seeing how things work, illness, virus tracking through populations. This is big data type stuff. This is HPC type stuff. Some of this, by the way, this is also big data type stuff. So this can be map reduced and other stuff like that, but that's a little bit different. Hey, Twisted Seed, how's it going? We're talking through some HPC talks that I did. I was setting this up all week, and I gave this talk to my Linux group down in our Discord today. But we don't have a recording of it, so I'm just kind of going through it again, and then if anybody wants it, they have the recording. Satellite imagery, you might have a big, 10 mile by 10 mile, satellite image, and you need to see all the places where something changed along a road or something like that for military applications and that kind of stuff. That satellite imagery, you would need to process that very quickly, and you would need to do that and turn that and get that turned around very quickly. So high performance compute is a big part of that kind of stuff. Also, slower versions of that, satellite imagery in the US is used. So when you have long running power lines that are running through forested areas, and you guys have probably seen how the limbs sometimes grow close, and then you can watch these online. There's actually videos of the helicopters will fly, and they'll just have these chainsaws hanging down. They're not always chainsaws, sometimes they're bladed saws, and they will just drag them along, and they'll chop all the tree limbs, right? So we'll watch this stuff happen, right? And satellite imagery is used to track that. Next time I post to HPC Reddit, I feel people there were really cool and know this exists. Well, that's awesome. Yeah, Mr. Nothing. I might do that one of these days. That might be kind of good. Yeah, branches. They chop the branches off, but with the big, they have like these big hanging circular and/or chainsaws in some cases, and it's pretty interesting. But they can track that with satellite imagery, and they'll check for change detection in the imagery between every 2 days or every 2 weeks to see where the branches are growing, right? So it's kind of a cool thing, and it saves man hours having to drive those lines, because it takes them hours and hours and hours to drive those lines, right? This is where I've done this. I built the newer HPC system for NOAA. I was a big part of it. I did a lot of the Ansible and the startup configuration and like the base images of it. But weather tracking, weather prediction, NOAA ingests from over 2 million sensors daily. So they have a tremendous amount of data coming in. And then, if you guys didn't know this, I have a link later in this presentation. By the way, this presentation's completely up in the Discord. So if you're like, hey, I gotta miss this, you can go download this presentation from the Discord with all the links. I got all kinds of links in this thing. To take you to different places. So feel free to join the Discord. It's down in the presentations channel. All right, so weather tracking is huge. Like, we got to run these weather data sets every 6 hours. Then those predictions go out. There's free and paid for versions of NOAA weather predictions and other things. They go out to all the different rural stations so that we can get better weather prediction. But if you've never thought of this,
And by the way, we send that to NOAA does worldwide weather, and the reason is because weather is tremendously important to military operations and logistics. I imagine it is important for countries as well to know. But yeah, other countries actually pay us for our NOAA weather. Like I know a lot of European countries, they get news feeds basically from our NOAA to predict what's happening with their weather. It's very important for your fishing. Yes, absolutely. But yeah, if you're ingesting from all this stuff and you have like 6-hour windows that you've got to present and create this data, you need a lot of parallel processing, a lot of data. A lot of that data also gets touched by this NOAA stuff. There's research scientists all over it running in the other cluster, so you always got a cluster up and then you got a backup cluster, and they're running against that. So we want to try to keep like an 80%, I don't know the exact numbers, and even if I did I wouldn't tell you the exact ones, but let's say like 80%. You want to keep utilization across those clusters. You don't want to just be sitting there, and you want to be keeping them utilized, practicing and training new models and testing and doing all this kind of stuff like that. The only one music is kind of noisy and difficult to hear. I can turn the music down. I didn't hear anybody say anything about it, but can you guys hear better there? Is that better? Turn the music down. All right. Yeah, I didn't even realize it was loud. Nobody had said anything. All right. Election tracking, people tracking, all kinds of things, right? And then, so this is how high performance compute's used. Is it all of it? Oh gosh, not even close. I mean, I've only touched the things I've touched, right? Like, and this is stuff that I've worked in heavily, but there's all kinds of other things. All kinds of stuff with HPC. So I'm going to show you guys the basic things that I can show you about how to get into this space, right? So we're going to start with system skills. These are Linux and system type knowledge that'll help you break into HPC work. So if you are already in Linux, or you're a hobbyist, and people come in all the time and they're like, oh, I know Arch Linux, and I'm like, excellent. Do you know how to do this, and this? Those are the things that are important as a systems admin. Well, a systems admin, a systems engineer will benefit greatly trying to get into HPC if they know these kind of things, right? And here's what I think your need to know skills are. So here's your need to know skills. Linux process evaluation. Do you know, right? So if you're on a system, what kind of Linux process evaluation can you do? Do you know how to do, like, let's say you do a ps-ef grep for SSH. Is SSHD running on this box? Yes, SSHD is running on this box. And we have a whole bunch of ciphers that are or aren't allowed. So maybe that's probably a custom way that somebody chose to run this. But can I tell when this was started? Do I know what the implication is that the parent ID of this is 1 and not something else? There's a certain thing that means in a system, right? If it's a 1 here, then it was started by the system, the kernel, when the kernel came up, right? This isn't something that was started later. These other things were started later, but they were related to SSHD, right? And then maybe some other things like, and when we get later on, whether or not it's running systemd, yeah. So later on, we're going to look at like some schedulers and some other things, and it'll help in troubleshooting if you understand what should be on in your system. Your system has a bunch of different things that should or shouldn't be on, typically like slurmd or mbatchd, depending on the system that you're trying to use for your scheduler. And all of the subordinate or worker nodes, some people call them slave nodes still, depending on which types of nodes you're working on, they need to have those daemons running so that they're listening to the master or the main or the primary, or some people call them, there's all kinds of names for these nodes depending on which different system you're also. Okay, so then there's the disk and mount points, right? So you need to know, like, df-h, what's that showing me? That's showing me how my system is carved up. This is important because if you're, and one of the things I'm talking about here with kickstart files, building RPMs, building software, kickstart files and how we carve up a disk is tremendously important for what we, when we build out a new box and we have a stateful or a stateless image, we're going to talk about those later, I expect them to be carved a certain way. I expect this disk to be maybe partitioned a certain way. this disk here has been partitioned a bunch, and this looks like, to me, that it's been partitioned according to like a CIS benchmark. So for a security reason, this has been carved up. But in HPC world, that's not always true, right? So our disk and mount points, it's kind of important that we understand what we're doing here and what we're looking at. I might want to know so I know this logical volume management. How do I know that? Because I'm using volume groups here. I can do PVS, VGS, LVS, and I can see that I've got my physical volume is just this one disk. I've got a pretty small volume group on that disk. I've got a pretty significant amount of that disk still free. So I could extend some of these if I needed to within my volume group, because I've got a lot of the volume group free, right? These are the kind of things that are kind of important to understand on the Linux side of things when we're getting ready to work in HPC world, right? Network and networking tools, right? So, I can do IP adder, and I can see that in this interface, in this system I have an ENO0, I've got an ENO2, ENO1, what am I thinking? ENO1, ENO2, and IB0. I've also got a loopback, but loopback is always there in any of your IPv4 type environments, and it's always got a 127.0.0.1 home address, right? But then I can look at this and I can say, well, I'm having a hard time getting out to the internet. I can't ping www.google.com. Can I? I cannot, right? Oh, I can, right? Took a while. But then I might look at this and go, okay, well, I need to figure out where my system's trying to send traffic. So I do an IP route. And then IP route shows me that if my system doesn't know where to send something here, it defaults to this address here off of ENO2. ENO2 is this address here. And I think about it and I go, So what I thought about earlier when we were talking about this was that this was my primary interface. This is not my primary interface. This is my primary interface because that's my default that the system sends traffic out if it doesn't know what to do with something. If it's going out ENO1, it's going to this address range. This is a tiny little /24 of only 254 usable addresses, right? My InfiniBand network is only 254 usable addresses as well, as is whatever this ENO1, maybe other address that's off of my ENO1 as well, right? So my point is I can start to figure out what's going on here. And if I'm a systems engineer or systems admin in a high-performance compute environment, I might need to be able to troubleshoot these tools. Let's say my InfiniBand isn't working right. I may need to do IB stat and see, what type of card do I have? Do I see that I have an active state with the link up? Maybe if I do IB status, I think IB status shows me the speed. Yeah, so I see that I got 100 gigabit per second 4x EDR type device. Maybe I didn't know that, right? And now I know that. And maybe I want to check that against all my devices to see what my devices' speeds are. So what I could do real quick, and I'm going to show these, actually I'll show it now a little bit, but XDSH to my compute nodes, and then I can do over on all my compute nodes IB status, and then I can do a grep for rate, and let's go ahead and throw this in a quote so it's all in there and it's not coming back after. And I can just run this real quick on all my systems, and I see that all my systems look like that. But I can also, and I'm going to show this a little bit later, I can do an XDSH back -C, and I can simply look for systems that are outliers, systems that don't have this 4x EDR, and maybe I need to be on EDR, not HDR or FDR. I don't expect anybody to understand all that now if you don't work in that space, but know that those are technologies and speeds that are kind of out there. Okay. So, yeah, this is a way that we use XDish. By the way, XDish is a set of commands that's specific to XCAT, and we're going to look at XCAT here in a minute. But we're back over here on Linux administration. People that got here a little late, let's just talk real quick. I'll pop this up. This is our stream goals right here. Learn about HPC and how to get skills in that engineering area. This is also in our Discord. So EDR, I think, stands for enhanced data rate, if I believe. I'm not 100% sure, but that's funny. We need to know file system permissions, right? Like, obviously, most of us doing Linux in some way could tell you something like ls-ld on root. We could look at this and go, okay, well, that's against the root home. That's the root's home directory. And over here, I can see that it's a directory. I mean, sometimes you've got the colors to help you. Oh, we're on an ad break, so I'll hang out here for a second. We'll check on Ranger Dog during the ad break. How's that? There's Ranger. Hang out with Ranger for a little bit on ad break. Ad break, Ranger check. There we go. I think the ads are running. It says the ads are running. Give a minute. I'll check my phone for a second, see if the wife's coming home soon. We'll pull this all out in post-production. I'm just kidding. I don't do any of that. I don't really do any of that post-production stuff. That's why you get what you get here. All right. Give it a second, and we'll get back to it. It's 30 seconds more, in fact. Yeah, Inspector, I get all mine off of Amazon for the most part. All right, am I back? Am I back from the ad break? We were just checking on Ranger during that. Okay, file system permissions. You need to know them. You need to have a general idea that, you know, this D right here says that I'm looking at a directory, even if the color doesn't help me out. By the way, not all operating systems give color like that, and your shell doesn't always have it anyway. So you can remove that from your shell with aliases, right? You should know that this is owned by root as the owner, the user owner. It's owned by the group owner of root, so the group owner is here. Read, write, execute. You only have read and execute as the root owner, and read and execute is all you have as the group owner of this root directory. Everybody else gets nothing for permissions, right? That seems really simple, but then you might say, well, do I have any FAC, let's see, get FACL, do I have any extended file system permissions on that? Whoops, root. And, well, are we using extended file systems? So mount grep. Root's not going to be on its own, but let's just do a mount and see in this system when we find the, we could look for it through, we can actually do it through, yeah, exattr, right? Grep. We could see if anything in here is using the extended attributes, right? And I think there's another one too. I always forget what it is, but the point is, you might want to know, you might want to need to know these things, right? And also one that I've seen turned off everywhere I've ever been, but some people swear by it. You just need to know your SC Linux stuff. As a general rule, you know, you do an ls capital L, capital Z on root, and you'll see if there's any permissions set and what we call labeling. It's additional labeling for access control. However, if we do SE status, we see that SE Linux is turned off, and we can do a more on SE Linux config, right, and see that it's also turned off. And then you can, if you needed to, you could redo labels and stuff like that. I showed that a little bit earlier. This isn't really the point of this, but you need to kind of understand these things. System building and boot process. Because the fact that a high performance compute system is almost always air gapped, we need to understand how to build our own RPMs. Sometimes we got to download software and build an RPM, and that package will then go to all of our different compute nodes. So sometimes we have to build our own RPMs. That's a skill you need to kind of learn and work with. We need to be able to build software from source. So if you've never done a configure, a make install, you know, make install and get everything working, and maybe go through, you know, dependency nightmare and have to go download new versions of libraries and stuff, that's a thing you still have to do in the high performance compute space. Everything is not in Yum or apt-get, and even if they were, they would be air gapped, so you wouldn't be able to get to them anyway. So Linux administration, those are things that are kind of important. Automation. Automation is using tools to extend your capabilities to multiple systems, right? So I wouldn't say that you need that in, I wouldn't say you need Docker much in HPC. I've only seen Docker like about this much in HPC, and it was with Cray's Shasta system, and then Cray's Shasta system's pretty much gone. Red Sly Fox, are you asking me about the RHEL cert? Or are you asking somebody else? All right. You need to understand how to loop and do system scripting tools. So, you should be able to loop over a set of systems and be able to, so if I do node ls compute, right, and I get this list of systems, I should be able to do something like this, for server in, I'll do it the more modern way, this way, right? Something like this, for server in compute. Oh, that's kind of low for you guys. Hold on. For server in $ node ls compute. Do echo. I like do it like this, checking $, so node compute. Oops. And then something like SSH compute, server rather. Oh man, what am I thinking? Server, and then SSH $ server, something like this, and then I'll say like host name or something. I don't know. Done, right? And then this will go and check all the nodes and see if it can get in them. But what server are you working with? Red Sly Fox, just because you ask. Certs. There's my certs if anybody cares about that stuff. But no, Red Sly Fox, none of this stuff is certs based. I'm showing you high performance compute stuff. So this isn't necessarily, I don't even know if anybody's got a cert for high performance compute. Yeah, those are all in the last 2 years, by the way. Well, except for the CISSP, I got that. Yeah, I'm kind of like a cert junkie, more for fun than anything. But those are my current certs right now. And then a list of the old ones down there. Okay, so yeah, and also, I mean, if anybody cares, I've been teaching this stuff for 15 years too, so at the college level, so so I'm trying to get through this, but this is a way to loop. The problem is, and they still haven't shown, no, I haven't seen any cool aliens yet. The problem with this though is there's not a lot of control along this loop that I'm using right here. It's just linear. It's just going to loop. It's not going to have. There's no error checking. There's not things that we get with other tools. But Perl and Python and Ansible. Ansible is one of my favorites for doing this stuff. Do I have Ansible on here? I don't have Ansible on here. If I had Ansible on this box, I could show you some Ansible commands. But the point is, I can hit all those nodes and extend my workout so that I can hit a bunch of systems instead of just typing and fixing things on one system one time. So looping and scripting tools are like key to this. They're very powerful at getting you to not just have to be one person sitting at the keyboard. You can, you can extend yourself to not have to be working all the time. You can just push stuff out, stage it, run it on different nodes. And then one of the things, I'm going to press up a few times because I'm lazy.
Hey guys, let me go over here to our chatting one. I do have to get off here. I got a work call in about 10 minutes. Most of you know I've been kind of co-working this whole time, even though I haven't been talking much because of my voice. But I might be on later, and if I do, I will try to, well, maybe I won't be on later because I can't really talk much, but I'll definitely be back on tomorrow because I'm getting a lot of stuff done while we're hanging out here. But we will try to catch up. We probably won't go right back into this stuff, but there is a recording of this. In fact, we're watching the same recording that I have up on YouTube already, so you guys can always go hang out over there. All right. I'm going to go find somebody to raid on the Twitch side of things, so hopefully somebody's up doing something there. And get this stuff out of the way. But hopefully this stuff's useful to you guys. Let me go find who is doing something fun. Oh, Rob's on. We'll go hop onto Rob's stream. So, man, my voice is going. All right, I'll talk to you guys here in probably sometime tomorrow. Take care. Or down in the Discord.